Good morning. Thank you for being here bright and early. Welcome to the second day of All-Inclusive AGN, Symposium 394. We will have our poster sparklers this morning for the participants that were assigned to present their posters in session 3944. Okay, so that's poster session 3944. Just to reiterate what I mentioned in the emails, all our poster sparklers sessions will follow the same format. We meet here for about 10 minutes in Ballroom West, and the presenters come up for 30 seconds and give the main highlights of their research and what they want to communicate. It also could be the location of their poster in the exhibition hall. And once we're done with that, we all proceed to the exhibition hall downstairs and engage with the poster presenters and look at the posters, etc. And then we reconvene back in Ballroom West at 10:30 to begin the oral presentations. So I would like all the poster sparkler presenters for this session to come up to the left side of the stage. When you see your poster up on the screen, you will come up to the podium and give a 30-minute synopsis of yourself, your research, and anything else you would like to communicate. Okay, if you've got more than one slide, just hit the next key and you'll go on to the next slide. Okay, you will be timed, just like in the board game, so try not to go over. All right, so Mupulusi, there you go. You may begin, and Kabelo will be checking your time.
This is the next.
Yeah, if you've got more than one slide, you hit next. Otherwise, just hand it over. And there's a pointer, laser pointer there.
There's a pointer. Yeah. Hi everyone, I am Mupurusi. My poster is about identifying interesting AGN in Dingo continuum images. So I used PyBDSF and Profound to find the sources, and then I compared these sources. After comparing the sources, I found a method that is able to find like the interesting sources from this. So those interesting sources are radio galaxies with features such as wide-angle tails and precessing jets. So that's about it that I have for today. I'm on poster number 36. Thank you.
Morning, everybody. My name is Antari Mahoro. So my poster is talking about AGN, or active galactic nuclei, in the Green Valley. A little bit I changed the talk because I got a poster. Then I was focusing on the oxygen 3 line tracing the outflows. The main objective of our work was to try to understand how AGN can quenching star formation, and the interesting result we get, it's the AGN in this Green Valley are enhancing the star formation rate, and our hypothesis, it's like our sample for AGN we have with infrared detection can happen.
Hi everyone, my name is Shelley and I'm presenting to you supermassive black hole mass measurement with molecular gas dynamics, so a little bit off the AGN topic per se, but if you come and visit me at poster number 55, you might find out why it's interesting for this community. It's a relatively new method. We look at luminous mass through MGE, multi-Gaussian expansion, and then get the kinematics of the molecular gas disk with the CO221 line with ALMA data. And this method is relatively new, coming online with exploiting the power of ALMA resolution power. I'm very excited to share this method with you. Come visit me at poster number 55. Thank you.
Good morning. My name is Rukaya. I'm a postdoc with Professor Marcus Bocher from Northwest University, South Africa. Our study focuses on BL Lacerta, a type of blazar. We modeled its spectral energy distribution and multiple light curves using time-dependent leptonic diffusive shock acceleration and radiation transfer mechanisms. So by modeling its ACDs of low and high flux states and light curves, we provide insights into the particle acceleration mechanisms. If this aligns with your interests, please visit screen number 19. Thank you.
Hi everyone, my name is Josephine Shala from Zambia, currently doing my master's in Botswana at BUS. I'm working on the major AGN and star formation connection in close galaxy pairs, considering the WISE data at 6 separations and 2 velocity differences. If you want to know the results we have so far and more about my work, you can check my poster at computer number 1.
Hello everybody, my name is Filippo Maccagni and I work at the Observatory of Cagliari in Sardinia, Italy. And this is the work about the Fornax-A and the Meerkat commissioning observations, then studying the continuum multi-wavelength from 84 MHz to 217 GHz. We could infer the spectral energy density distribution on the left and say that this AGN activity is flickering while combining H1 that you see in blue in the figure, molecular from ALMA and ionized gas information from MUSE, we could infer that the fueling of this flickering AGN is given by infalling clouds. Thank you.
Hi everyone, my name is Miura Rangianasi and I'm a MSc student from the University of Antananarivo, Madagascar. And the title of my project is Investigating Radio Properties and Star Formation Activity at the specific redshift. So I invite you to come to my screen on screen 33. Thank you.
Good morning. My name is Jiří Svoboda and I'm from the Astronomical Institute of the Czech Academy of Sciences in Prague. And here I present the poster linking AGN accretion states with properties of host galaxies. What we do is that we study AGN accretion state in analogy to X-ray binaries, where they change the states between hard state with the jet and soft states with the accretion disk. And similarly, we look at the radio AGN, and also they occupy different position in the hardness luminosity diagram based on the radio morphology. And most recently, we looked also on the relation between accretion states and the star formation rate. So if you're interested, you can see the full poster 1045 or now at the stand 84. Thank you.
Hello everyone, my name is Tumb and my poster is on the search for restarted radio galaxies, which are radio galaxies that have multiple signs of nuclear activity, and I'm using Meerkat and UGMRT data to look for them, and I use those following criteria, and these are the most interesting sources that I've found. And if you want to see more, or if you want to know more about the nuclear activity cycle of radio galaxies, then you can check my poster screen 31. Thank you.
Hello, I'm Yusi Kim from Gyeongbuk National University in South Korea. The neutrino blazar is the third discovered astrophysical neutrino source after the sun and supernova. Because of the characteristic of the neutrino with no charges, so we can better trace the origin compared with electromagnetic and cosmic ray. To understand of this type of blazar, I analyzed the jet kinematics, and my poster represents the result. If you're interested in my research, just remember the keyword, the neutrino blazer. Thank you.
Hello, my name is Michal Zajaček. I'm from Masaryk University, Czech Republic. And in our project, we studied how we can turn quasars into standardizable candles. And currently there are two relations, X-ray UV luminosity relation and broadline region radius luminosity relation. And we identified sample of 58 quasars for which we could study both relations to see if there are some systematic differences. And we found that actually there are some differences, that X-ray UV relation prefers larger omega meter parameter than radius luminosity relation. And generally the distribution is asymmetric of luminosity distances. And this can be attributed to extinction, as we present in our papers and poster. And you can see me then downstairs for more information. Thank you very much.
Okay, it seems we've reached the end of our posters. If your poster is not here but you want to advertise, you feel free to come up and speak for 30 seconds. Sorry? Yeah, I think this is the end. So can we give a hand to all our speakers and go support their posters downstairs?
All right. Good morning, everyone. Welcome to the second session, second day of this wonderful symposium. I'm Lucia Marchetti. I'm a senior lecturer here at UCT. You might have seen me already in Division J. It's always me. So today I'm going to chair this session, and it's my pleasure to invite our first speaker of today, our invited speaker, Nicole Thomas from Curtin University in Australia, who she's going to talk about radio galaxies in cosmological simulations. I'll give you 5 minutes.
Is there a clicker? Is it the clicker? Good morning. And firstly, I'd like to thank the organizing committee for inviting me to share my research with you. As mentioned, I'm Nicole Thomas. I'm a Jim Bucky Fellow at the University of Western Australia, based at the International Centre for Radio Astronomy Research. I'm originally from Cape Town, so I'm very excited to be here and be home. So I'm going to tell you about radio galaxies in cosmological simulations, but I'm going to take it back a little bit first, all the way back to evidence of black hole galaxy coevolution. So observations show us that the properties of black holes correlate tightly with the properties of their host galaxy. So as an example, this is from the review of Cording and Ho, which shows that the mass of the central supermassive black hole correlates tightly with the bulge properties of its host galaxy, indicating that there is some sort of related growth between the two sources. But not only do these correlations exist at low redshifts or at local times, but this does also persist over a large range of redshifts. So what we're seeing here is the standard star formation rate density over cosmic time, shown by the data points and this gray band. But what we also see in this plot is this black line that I hope you can see clearly, which shows the black hole accretion rate density over cosmic time, relating very closely to the star formation rate density. And we see this both in observations, so this middle slide, or middle plot rather, as well as in simulations. So this is from the SIMBA simulations, which on the bottom shows that same relation where the blue points and this blue dashed line shows the star formation rate density over cosmic time, and the orange line is the black hole accretion rate scaled by some factor. So really indicating that the growth rates of both black holes and star formation within the host galaxy is closely related across cosmic time. And further, what's really important in regulating these relations is jet mode feedback or radio mode feedback. So this is when these AGNs start launching these relativistic jets. And what we see is that imposing these AGN feedback in simulations is required to reproduce observed galaxy populations, various galaxy properties, and black hole galaxy correlations. As an example, on the left, I'm showing the galaxy stellar mass function from the SIMBA simulations, which essentially shows you from, sorry, there's a little bit of an echo and it's throwing me off. So showing from redshifts 2, 1, and 0, that if you do not account for jet mode feedback in simulations, you tend to overproduce the number of high mass quench sources, shown by this blue dotted line. And then once you do impose your AGN feedback within these simulations, you're able to recover the observed galaxy stellar mass function showed by the green line. And not only is jet mode feedback important on these galaxy scales, they're also important for regulating the cooling of clusters, shown by the schematic in the center. And these radio sources come in all sorts of shapes, sizes. So here's some examples on the right. We saw some examples of this yesterday as well. And it's thought that the morphologies of these sources, the brightness, the sizes, is actually regulated or controlled by the inner regions surrounding the black hole. So at completely significant orders of magnitude smaller scales than over which these jets actually are populated. So what do I mean by that? So typically, radio galaxies can be divided into two general classifications. So these are your radiative mode AGN or your jet mode AGN. These can also be referred to as quasar mode, cold mode for the radiative mode AGN, or hot mode for the jet mode AGN. And essentially, the key differences between these two populations, or at least so we think, comes down to the central regions surrounding the supermassive black hole. So for the radiative mode AGN, you have the black hole at the center surrounded by your typical accretion disk from which you have this cold mode fueling. And these sources typically are observed as AGN across the electromagnetic spectrum. So you see high excitation lines in your optical spectra as an example. So these are also referred to high excitation radio galaxies or HERGs. And they're typically observed in fairly large galaxies, but still with some ongoing star formation. Whereas the jet mode AGN, which you would think of as your typical jet mode AGN, these don't show AGN features at other wavelengths, so it's thought that they accrete via some advection-dominated accretion flow, or perhaps some chaotic accretion that would disrupt your accretion disk. So you do not see accretion disk properties in these sources. And so these exist in massive elliptical galaxies that typically don't have much star formation. And these are referred to as low excitation radio galaxies because they do not exhibit those high excitation lines in their optical spectra. So these are referred to as LERGs. So I'll probably go between calling these HERGs and LERGs, or cold mode and hot mode, based on the accretion flow. And it's been thought for a long time that you could differentiate between these two types of sources based on their Eddington rates. So HERGs or radiative mode AGN tend to have Eddington rates of more than 1%, whereas contrary for the low excitation radio galaxies, they have low Eddington rates. But this comes from some rather older studies, which can be seen here. So this is based off of the Besser and Heckman 2012 observations, which show the low excitation radio galaxies in this blue distribution, the high excitation radio galaxies in the red distribution. And this basically shows you the Eddington rate distributions of these sources. And what you see is this very significant bipolar distribution between the two populations. But then at some later point, we had access to deeper and fainter observations. So this is from Imogen Whittam's work in 2018 when they looked at the stripe 82 field. And what you see is as you go to these fainter luminosities, this dichotomy becomes much less apparent. There's a lot more overlap. So indicating that maybe as we probe these fainter populations, we will see less of the so-called dichotomy. So this presents a few questions. Firstly, if not the Eddington rate used to classify these sources, then what are the physical processes that actually give rise to the global features of these two populations? And how do we expect these features to evolve into, one, the faint population, but also over cosmic time? We have been limited to redshift information as well. But I'll throw in a third question as well, asking, can we use cosmological simulations to reproduce these demographics in any way? And considering the title of my talk, I'm assuming you know where I'm going with this. So we use the SIMBA simulation. So SIMBA is a cosmological hydrodynamic simulation, which includes dark matter, gas, stars. The fiducial box is about 100 megaparsec per side. And what's incredibly unique about SIMBA is that it imposes this dual mode accretion model, which is typically not done within a cosmological simulation. So SIMBA includes a hot mode accretion in the form of Bondi accretion, but it also accounts for the disruption of angular momentum in your galactic disk that drives cold gas down to the central regions in the form of this torque-limited accretion. It also includes a physically motivated model for AGN feedback, specifically in the form of black hole winds, bipolar jets, and X-ray heating. And it's been successful at reproducing a large number of black hole galaxy correlations as well. And you can see on the right side the impact of imposing this AGN model on the simulation of the galactic medium. So this shows a temperature map for redshifts 2, 1, and 0, including, that's a bit shaky, including the jet mode feedback, but also excluding it. And you can see how that impacts the intergalactic medium. And just up there in the inset is a realistically looking jet mode AGN as well. So knowing that SIMBA has this unique model, we can actually use this and directly test, if we go back to our radio galaxy dichotomy, understanding whether the impact of the accretion mode can result in the demographics of these two populations. So again, using the idea that HERGs are cold mode accretors and LERGs are hot mode accretors. So what does that look like? So again, just to mention, we're taking the SIMBA simulation, essentially identifying all galaxies that are undergoing jet mode feedback, separating them between whether they're hot mode dominant or cold mode dominant to define high and low excitation radio galaxies. We can then take a measurable within the simulation, so in this case, the black hole accretion rate, scale it and to estimate some radioluminosity. And that gives us a radio galaxy population that reproduces and matches to the observed radioluminosity function at these very low luminosities. And we can account for them in terms of the star formation emission, as well as the AGN emission, but also separate them into what would be star-forming galaxies and quiescent galaxies. And the initial predictions that came from this study, this very basic test, was that at least at redshift 0, as we probe these faint luminosities, the global properties of radio galaxies essentially become indistinguishable between the two populations, apart from the star formation of the host galaxy. Specifically, we find that above a certain radioluminosity, there's a turnover in the star formation rates of the lurgs where they start becoming quenched. At this time, we weren't able to do any direct comparisons with observations because there were no observations that existed at these low luminosities, but we are very excited to now have the MIGHTY survey. So for those who don't know what MIGHTY is, it is a radio continuum survey on the Meerkat array. It covers several survey fields that have a multitude of multi-wavelength data to really get into the demographics of these populations. And their goal is to probe the evolution of AGN and star formation over cosmic time. But what's really incredible about this is now we're starting to really probe this very faint region of the luminosity space, but also really deep as well. So we wanted to take SIMBA and see if we could reproduce what we're starting to see with MIGHTY. So we basically take a SIMBA light cone, match it in the luminosity redshift space to that of MIGHTY, select radio excess sources. In MIGHTY, HERGs are selected as those that are defined as AGN at other wavelengths. And then again, LERGs are those that do not have AGN signatures. And I'll just basically go through some of the very brief results we have so far. So what we see is, so on the left is the full MIGHTY sample. On the right is the SIMBA sample, so in these shaded bands, with the MIGHTY sample limited by Eddington rates of less than 2% to coincide with the SIMBA simulations. And what we essentially see is that the host galaxy's stellar masses between HERGs and LERGs are indistinguishable across all redshifts. What we also see, very interestingly, is that at the lowest luminosities, the star formation rates of these sources are pretty much indistinguishable. However, once you get to luminosities of about 10 to the 23 watts per hertz or so, we start seeing this turnover in the LERG population as we had predicted before. Further, if we then look at the Eddington rates, I've been talking a lot about Eddington rates. Again, on the top left, we have the MIGHTY sample. LERGs are this orange color, HERGs are blue. The dashed line are the Besson-Hickman 2012 results, which show that initial distinct dichotomy. And then these vertical lines are just values of 1% and 2%. On the top right are the SIMBA galaxies. Bottom right are MIGHTY radio galaxies limited by the Eddington rate. And then before I get to the bottom left, what we already see is that there's just complete overlap between the Eddington rates of these two populations, which is already in contrast with those initial observations of having a radio galaxy dichotomy. So the question is, where does this start becoming apparent? Why does this overlap exist? So if we go limit our sample back to where the Besson-Hickman sample was observed, so at redshifts less than 0.75, what we see is a very distinct population of high excitation radio galaxies popping out of the observations. So this implies that below some luminosity threshold, this radio dichotomy that we've observed in past and that has been very impactful for many models starts to disappear. So what does this mean? So a physical interpretation of what it is I'm trying to explain is that if we believe that HERGs and LERGs are fueled by different modes of accretion, cold and hot mode, then what we expect is that the cold gas supply within the HERG host fuels star formation within the host, but also supports the cold mode accretion, giving rise to those accretion disk features. So that's maybe not so surprising in terms of just the typical AGN model. LUGs, however, have low gas fractions within their hosts. So this means lower star formation rates, but also more indicative of hot mode accretion, which results in the lack of these accretion disk features. And this persists across luminosity and across redshift. So the question is, are these two populations distinctly different in this way? Does one evolve into another population, or can you go through various phases of these different populations? But that is a whole another conversation that we can always talk about at another stage. But before I get too carried away and make too many bold statements, there are lots of caveats associated with doing these comparisons and doing this, these tests. I'm not going to focus on all of them because, again, we will be here for a very long time if I try to. But some of the things that we're trying to address directly is, one, the case of having slow jets within cosmological simulations. So these jets are not relativistic, and so we need a more realistic way of imposing jet mode feedback within simulations. And additionally, we need to be able to do better estimations of the radioluminosities rather than just a scaling relation. So one of the things that we're doing at the moment, and this is actually being led by one of our students over at ICRA, Nick Marigakis, who's looking at launching radio jets within various media and across different types of code to understand the best way of implementing radio jet mode feedback within cosmological simulations. And this is just an example. And can I play again? No, okay, there we go. So this is just an example from the Pluto simulations. And what we hope to do is then implement these jets into some of the Zoom simulations that we're currently running over at ICRA as well. So these are the SOLAS simulations, which will be a suite of Milky Way Zooms so that we can implement this jet mode feedback, but also other black hole physics as well. And then further, because what this will help us, is the fact that within cosmological simulations, there's no way that we can actually get down to the central regions of the black hole because we do not have the resolution to actually model that physically. So we use subgrid models. So hopefully with improving our resolution, we can get maybe better constraints on the physical processes that model these accretion flows and jet mode feedback. And then further, another big problem we have is low number statistics. So yes, we are working with cosmological simulations. There are lots of galaxies in cosmological simulations, but the moment you start cutting your populations based on whether they need to have certain criteria, imposing flux limits, selecting radio excess sources, you end up with very few numbers actually. So one of the things that we're hoping to do is impose these models into a semi-analytic model essentially so that we can map these into much larger simulations to get better number statistics and overall population statistics. So with my last 1 minute, I'll ask, can we use simulations to actually reproduce the demographics of radio galaxies and understand them better? I'd like to think we are starting to. So lots of this work is all very much starting, but it is in progress. But what I will leave you with is the fact that combining various theoretical models of radio galaxies is a powerful tool to actually understand the physical processes driving black hole accretion feedback and how it interplays with the host galaxy specifically. And it's vital to connect these different models to observations and vice versa, one, so we can constrain our models in a much more realistic and physical way, but also so that we can use these models to not just make predictions for upcoming, say, radio surveys, but also to better interpret our observations, especially once we have, the full SKA, we will be completely inundated with sources that'll be very difficult to understand directly what the physical processes within these sources are. So really, there is no time, unlike now, to really be doing the science. So I'll stop there and I'll take any questions. I was keeping my eye on that clock. I thought I was out of time. Oh, amazing. Okay.
Really nice talk. Thank you. I was wondering, when you were saying you were splitting your SIMBA sample between the ones that were cold mode and hot mode dominated. I wondered if you could just say a little bit about over like what time scale you were looking at, like, yeah, how you did that split.
Yeah, thank you for that question. So essentially what we do, because Bondi accretion in cosmological simulations can be very stochastic. So initially what we did was just look at this from an instantaneous accretion point of view. We realized that's not the best way to go about it for that reason. So essentially what we do is we have really high time resolution accretion rates for the black holes within the simulation. So we average the accretion over 50 megayears. We tested a few different timescales as well, and 50 megayears seems to be consistent, one with the dynamical time of the black hole, but also it's a period over which the torque accretion, which is actually quite stable. So also just for context, the black holes undergo both Bondi and torque limited at the same time. So it's over 50 mega year period, and we basically just very simply say if it's dominant in the cold mode, so more than a certain fraction, then that is a cold mode accretor, and that's a HERG.
Thank you.
If I may, when you ask your question, if you can say who you are and from where you are, because people online would like to know as well. Thank you.
Hi, I'm Johnny Pearce from University of Hertfordshire, but Nicole knows me already. So, so I wanted to ask if you'd mind going back to the mighty star formation rate versus radioluminosity plot.
Oh, that one.
This one, yeah. So I was wondering at the highest radio powers there, you've got very high star formation rate for those couple of points. And I was just wondering, because that's, I guess, not what you'd really expect. I was wondering if there was any particular reason for that.
When you say for a couple of points, do you mean specifically?
Like 10 to the 26 on the left-hand plot I'm looking at, 10 to the 26, just above that.
Yep.
10 to the 27 is where you got log star formation rate at 10 to 2 to 3.
Yep.
Yeah.
So again, that's a problem of, again, low number statistics. What's plotted here also is the standard deviation error rather than anything else. So essentially what we're seeing here is like there's maybe a few points over here, so the error bars aren't very big. Technically, they should be a lot bigger than they are. I wouldn't say that it's not that we expect them to sort of fill up this region. I know a lot of the high excitation radio galaxies in the mighty sample are star-forming galaxies. Again, these are radio excess, so that's why you see the envelope on the left side. So I think they are consistent with what you would expect, but again, I can't comment on that directly because I'm not entirely sure what you mean.
Okay, all right, thanks.
Sabina Belstead, ICRA as well. Just while we're on this plot, very brief question. Do you know those star formation rates from MITI, whether they're radio-based or optical-based from ancillary data?
The star formation rates, I believe, are optical through to infrared.
So some sort of broad SED fitting based
Yeah,
star
SED
formation
fitting,
rate.
yeah.
Okay, perfect. Awesome, thanks.
Hi, I'm Sarah Markov from University of Amsterdam. I really liked the talk. Thank you very much. It was interesting because, X-ray binaries have black hole mode switching, just like you have jet modes and non-jet modes, and they don't happen at the same accretion rate. So that could explain your overlap in population. I was just wondering, have you ever thought about trying to mimic that in your simulations?
So doing that, so what we're looking at the moment is essentially, to some extent, what we would call the duty cycle of these AGN. Again, you need a really good time resolution to actually do that. Because one of the things that I have thought way too hard about is, the timescales over which these populations exist, the correlations between the jet and the actual time of jet launching, which does pose problems for trying to do these comparisons in a logical way. So we are looking at the So essentially the fluctuations of Eddington rates within the sources, some of them do, and I can show you some of this maybe at a later stage, I don't have it with me, but some of these do, go into this jet mode and they stay there. Some will go into the jet mode and then go back into off. But what we see is most of the lurg type sources tend to just stay in this quenched jet mode for very long periods, whereas the HERG sometimes do tend to go in and out of phases. So this is something that we're looking into, and trying to be able to quantify those timescales is something that we are currently working on, but that I think definitely needs a bit more thought to really get into those details.
Hi, I'm Ranieri Baldi from Institute of Radio Astronomy in Bologna. A nice talk. I have a comment about the lack of bimodality of LERGs and HERGs at low luminosity. You need to think about that. If you go to low luminosity, the contribution from radio-acquired AGN can be dominant. And so probably there are many sources that you are classifying as radio galaxies, but actually, as you said, with low jets and sublativistic jets, they're not actually radio galaxies, are not radio loud AGN, but they are radio acquired AGN. It might have a different cosmological evolution from the LERGs and HERGs population. So if you include them, you might have some issues in modeling the population because the contribution can be dominated by radio acquired AGN at low luminosity. So can you have a comment?
I can respond, and thank you for that comment because I do agree with that. This work specifically, or especially from the MITE point of view, is specifically radio loud AGN. So these are selected to be radio loud, radio excess as well. So we are confident that these are radio loud AGN. So this dichotomy still exists, again, still in this very faint population. I think what's really important to also keep in mind is not only the contribution of radio acquired sources, but also the interplay between the AGN and the star formation specifically. So I think we're getting to a region or an epoch of radio galaxies where these two components become a lot more impactful on each other, and maybe the interplay between the two processes are a lot more, sorry, I can't get to the word that I'm looking for, a lot more important that we maybe think they are. So I think, yes, this is something we do need to take into consideration, but I think this is definitely something that will be looked into further. From the observations, I cannot comment as much, but again, from the simulations, we can, try to study the interplay between the two so that, again, we can make more insightful predictions for these upcoming surveys that will really be probing these very faint, deep luminosities.
Thank
you. Thank you.
Thank you, Nicole. In the interest of time, we need to move on. So next speaker is Atsushi Hoshi, who is going to talk about the relationship between supermassive black hole and their host galaxies and intermediate redshift in the variability selected AGN sample. For the tech people, there is a really bad echo here. So I don't know if you can do anything, but it's really annoying for the speakers. Just saying. Okay. I'll give you 2 minutes.
So good morning, everyone. Thank you very much to the organizers for giving me the opportunity to present our research. I'm Atsushi Hoshi, I'm a PhD student at Tokyo University in Japan. So today, I talk about black hole galaxy relation using variability selected AGN. So first, let me explain a brief introduction. There is a black hole, there is a type of correlation between a black hole and tight correlation in the local universe, as you can see in the right figure. However, it remains unclear how the supermassive black hole grows from the seed black hole through their interaction with their host galaxies. So our scientific motivation is to understand how they evolve into the local black hole bulge relation as we can observe today. So I also explained the scaling relation and its morphological dependence. Right figure shows the black hole and stellar mass relations. and which is more scattered compared to the black hole bulge relation. And I also I'd like to highlight that this scaling relation depends on the morphologies. For example, late type galaxies generally possess larger stellar masses compared to the early type galaxies when compared to the same black mass ranges. So regarding the scaling relation for the AGN, there are several perspectives on this topic, but the recent study shows the black hole and galaxy relation doesn't evolve up to, let's say, up to 2.5. In light figure, blue regions shows the active AGN up to 2.5, but it's unclear in the region of the low mass region. So it is necessary to search for the low mass black hole in order to understand the origin of the coevolutions. So at the high redshift, so massive black hole are typically observed, particularly beyond redshift 4. So before JWST, AGN with low mass black hole couldn't be detected by the ground-based telescopes such as ALMA and HSC. But recently, JWC has revealed that a faint AGN with low mass black hole with black hole mass 10 to the 7 or 8, which is also show the overmassive system compared to the local universe. So there is a still ongoing debate about whether the overmassive system being preferentially detected due to the selection effect or not. So let's move on to the agent variability. So it is well known that AGN play a very important role in understanding the black hole growth and galaxy evolution. And also, it is well accepted that AGN most AGN shows variability. Their reasons are considered, such as disk instability and the inhomogeneous disk model, and also the changes of the accretion rate. But the primary origin is still under debate. So I will explain the two advantages of optical variability agent selections. So it is empirically known that agent selection shows the larger amplitude in at the lower luminosity. Considering that the biliary black hole mass depends on the agent luminosity, we can explore the low mass black hole if we can detect the low luminosity AGN. Secondly, this method can essentially select only the type 1 AGN because we can only detect the optical compact region, which is not obscured by the dust torus. So this means that it is not require the threshold for a broad line in order to separate from the type 2 AGN. So in estimating the biliary black hole mass, this method is a very effective way to explore the low luminosity AGN and the low mass black hole. So from this slide, I will explain our studies. So the selection method is very simple. Using Subaru HSS SSP survey in the Cosmos field, variable AGN are selected by the detecting the flux variability amplitude. But of course, there are other detailed methods to distinguish it from the supernovae, but I will skip it here. So this is a summary of the AGN value. This is summary of our sample. Roughly 500 variable AGN are selected, including with those with the I1 magnitude 25.9, and let's shift up to 4.5. So interestingly, among the selected AGN, 50 objects were not detected by the X-ray. So, but however, X-ray stacking analysis have revealed that they are hard X-ray sources. So, which means that most X-ray undetected, but the optical variability selected objects are considered to be AGN. So the purpose of this work is to measure the black hole mass and the stellar mass and investigate the black hole and galaxy relations. So in order to estimate the black hole mass, we need velocity width and AGN luminosities. So the velocity width are obtained from the archival scopic data. So right figure shows the 6 example of the borderline fitting results. So AGN luminosities are converted from the hard X-ray for the X-ray detected object, but from the SED fitting result for the X-ray undetected variable AGNs. So this is the result. Blue and red circles show the X-ray detected and X-ray undetected variable samples. So as a comparison, we also plotted white circles. This sample is detected by the X-ray in the same regions. So, and also the colored solid lines shows the black hole detection limit as a function of redshift, assuming the detection limit of X-ray and the threshold as known borderline width of 2000. So this result shows our samples can cover the wider redshift up to 4.8 and the lower black hole mass compared to the only X-ray detected samples. So the deep optical variability selection enable us to explore the low mass black hole. So this is the black hole and the stellar mass relation. The black solid line shows the black hole and multi-mass relation in the local universe, and the red and blue dashed line represent the black hole and stellar mass relation for the early type galaxies and for the late type galaxies. So our sample is widely scattered, and there seems to be no strong correlation. So there are possible reasons, such as, for example, wide black hole mass ranges, morphological dependence, redshift range, and also stellar mass error from the SED fitting. Stellar mass estimated from the SED fitting. So we will discuss whether black hole and stellar mass ratio varies with redshift in our sample. So since there is no strong correlation between black hole and stellar mass, leading that the black hole stellar mass ratio apparently depends on the supermassive black hole mass. So we classified our sample based on the black hole mass in order to classify our sample based on the black hole mass before we investigate the redshift evolutions. So we found the black hole and stellar mass ratios doesn't show a significant redshift evolution in each redshift being in each redshift. But regarding the population of the very high massive black hole and very low mass, less mass black hole, we couldn't investigate the redshift evolution due to the limited sample. So here we compare our sample with the local and high sample. So when we see the very overmassive black holes, many of them show the very high ratios compared to the local bulge and bulge to black hole bulge ratios. So So this means this suggests there is an existence of the fast black hole growth path. On the other hand, we focus on the less massive black hole. These black hole stellar mass ratios doesn't change between intermediate redshift and the local universe. However, the black hole stellar mass ratios for the high G AGN shows very high values. So which implies the host galaxy harboring less black holes have already acquired sufficient stellar mass at the intermediate and local universe, but the high G galaxies are still in the early stage of the galaxy formations. So this is a summary. If you're interested in the work, so please check our papers. Thank you very much.
Thank you very much. Question? Yeah, we have time for a couple quick ones. So please remember to say who you are, just for the audience online as well.
Thank you very much. I'm Izzy, I use they, them pronouns, and I'm from Masaryk University almost. I start next week. I want to quickly talk about how you got the black hole masses, because you've got the three sort of constants in there, I think they were, A, B, and C. I was just wondering what those were and what they physically represent.
So,
yeah.
So black hole mass?
Yeah, so you've got A, B, and C in your thing. How are those constants determined?
I checked the black hole was consistent with the estimates from the X-ray or SAD fitting result or whatnot. So is it? Can I answer your?
So do the constants, the A, the B, the C, do they have a physical representation?
Yeah, ABC.
Yeah.
Okay. ABC is different. I'm using a different value in each line. So and this line is same X-ray luminosity and using the same velocity. We can plot the we can plot the same black hole mass as a function of redshift. So this means the very consistent with the black hole mass using in each line.
Okay, thank you very much.
Hi, Louis Ho from Peking University. Your stellar masses, I wonder how you obtained them. You said SCD fitting, but these are by selection type 1 AGNs.
Type 1 AGN.
So how did you account for the contribution from the AGN into your photometry?
There are yes, stellar mass estimate from this. Actually, there are some contributions of the host galaxies, but there are some uncertainties of the determination of the stellar mass. But I think it's a good estimate the S3 fitting. So and all, but I think it's there are some uncertainty, and including the large errors. So.
Stop you here, but I think you can continue this discussion offline. I think, it's important to have a look to those stellar masses as well. Anyway, so next speaker is Jacques. Here's coming. So Jacques Smulders, who is going to talk about goal-oriented stacking, selection of AGN host galaxies below the radio detection threshold. I'll give you the 2-minute warning.
Cool. Hi, everyone. My name is Jacques. I'm a second-year PhD student at the University of Witwatersrand. And this presentation was going to be pretty much in two parts. So firstly, I'm just going to introduce this really cool algorithm called goal-oriented stacking. And then we're going to go into a flagship first application of this algorithm, which we have used for selection of radio-quiet AGN. Ready. So just a quick content. I hope this presentation will be sweet and short. So as I said before, going to give a quick overview of Go stacking, just quickly go over the data products, mainly using radio and X-ray data. And then we're going to look at how we actually selected radio-quiet AGN, as well as some diagnostics to show, are these actually radio-quiet AGN that we're looking at? So first, I just want to elaborate what I mean by radio-quiet. So conventionally, if you have your Euclidean source density count over there, when we refer to radio-quiet galaxies, it's generally galaxies that exist below this tens of microjansky regime. So these are galaxies that are typically too faint to be detected individually in the radio regime. So we usually resort to stacking to actually study the statistical aggregate properties of these galaxies a bit further. So just a quick description of how stacking generally works. So we have some parameter space of galaxies. In this case, we just have a simple specific star formation rate as a function of redshift. And we make a heuristic selection in the parameter space. So for example, here, we just take some square, select a region of galaxies. These could be quiescent, most likely in this case. And each galaxy is optically and infrared detected from a multi-wavelength catalog. So we know where these sources are. So we just take those corresponding positions in a radio survey map, draw a sub-image, and we stack these sub-images, and then we can investigate the properties of these stacked images. Now, what we propose to do with goal-oriented stacking is we instead reverse this whole process. We want to impose a sort of heuristic objective on the stacked radio map. And by doing that, we can sort of have an optimization problem where we want to select our sources such that some objective is met. And we can actually then reverse and see, okay, now what does the parameter distribution look like? So just a quick schematic of how this generally works. So we're looking for a bunch of galaxies in the radio quiet regime. And we select these sources using a neural network. We just use a neural network because it's a very nice decision tool. And we feed the inputs that we feed into this neural network are the catalog parameters of these sources. These could be redshift, star formation rate, stellar mass, any derived properties. The neural network makes a decision. Are we going to select this galaxy, or are we just going to discard it? And once it's selected a sample, we can take the radio sub-images of these galaxies, stack it, and then impose some objective function on the stacked image. Now, the real power in this goal-oriented stacking is the objective function that we actually employ. For example, a very straight off the bat objective function would be maximizing the signal to noise. And this is actually any function that has the signal to noise intrinsic to it. Because I think one of the main concerns with stacking is we don't really have a lot of signal. So if we can maximize the signal while also maybe extracting some profile from the stacked image, we can actually end up selecting really cool galaxies. So a quick overview of our catalog and input parameters. So we use the Cosmos 2020 multi-wavelength survey. We only consider 70% mass complete samples. This is just to have a nice unbiased sample. We remove all our radio and X-ray far infrared detections. This is so that we don't have any skewed results in our stacking because we want to look for sources that are radio quiet. And if you want to know the parameters that we do use as input for the neural network, these are our conventional redshift, stellar mass, star formation rate, and some bands that are proxies for stellar mass and star formation rate. The two telescopes that we use, VOA 3 gigahertz and the Chandra hard band. And this is the first approach that we employ. So this is going with a first straight off the bat approach. We want to maximize the signal to noise of our sample. And we maximize radio and X-ray. I think the motivation is pretty clear. If we are going to select radio quiet AGN, if there is AGN activity, we do expect a combination of radio and X-ray signals going hand in hand. So we simply employ a linear combination of these two. So you'll see F of our subset selected is just the signal to noise ratio in the radio band plus the signal to noise ratio in the X-ray band. That third or that second term, that's just a regularization factor to help with the training. you can just ignore that. Right, so this is the sample we end up selecting. So we have a sample of around 20,000 sources once optimized, and we see we have these nice detections. I should probably first elaborate. So each column is a redshift bin, 0 to 1, 1 to 2, 2 to 6, and each row is a stellar mass bin, 9 to 10, 10 to 10.5, 10.5 to 11, and 11 to 12. So we see here we have these nice signals at low redshifts, large stellar masses, except for that top right bin. I think just one source was selected. That's fine, we just excluded going further. And if we look at our star formation main sequence, we can see that our sample, contains a lot of starbursts, right? These are massive galaxies. Not really much more we can say about this, but it's just nice to know where these galaxies lie in the parameter space. To check if these are AGN, first approach, we can just check where do these lie in the IRAC bands, looking at the Donnelly and Stacey selection criteria. And as expected, there's not really much sense to be made from here. I think this is just more to show that we are going to need more sophisticated techniques to actually successfully classify these galaxies as radio-acquired AGN. But what we can do is we can look at the radio or the excess radio emission. So we take the observed luminosity in these redshift stellar mass bins, and then we just compare the star formation rate converted to radio emission. So just keep in mind the star formation rate in the multi-wavelength catalog is optically and near-infrared derived. So we can safely convert that to radio, and if we see that it doesn't match with what is observed, that excess emission should most likely be from AGN activity. So to investigate these AGN properties in the best way I could think of, we looked at the fundamental plane of black hole activity. So there was a really cool paper by Yuzhen Wang and Tao Wang, where they took a population of radio-acquired galaxies, and depending on whether this population was Hurgs-Lurgs, or whether the host was star-forming or quenched, they were able to fit a locus, and I basically took that locus and found which of these loci fit closest to my points in a way that we could maybe classify these samples in their redshift and stellar mass bins as either being low energy, high energy, or star-forming host, quiescent host. And these are just some of the process. So naturally, we subtract the star formation rate from the radioluminosity. From the X-ray luminosity, we subtract the XRB component, and we assume a photon index of 1.8. And we just vary the column densities and just include that in the errors to see how far the X-ray luminosity can vary. Right, so there's our fundamental plane. As we see, we only actually have, well, if you don't see a plot in any of the redshift or stellar mass bins, it means that the observed radioluminosity was either not high enough to still exist if we subtracted the star-forming component, or it means that the X-ray luminosity was just too noisy. So we see that for our high stellar mass galaxies, it lies within 1 sigma of this locus. And we can maybe try to make some sort of analysis out of this. Keep in mind that we are keeping starbursts in this population, and that'll become a bit important later. But we do see there does seem to be some evidence of this high mass population moving from a state of being low energy at high redshift, and as it moves towards redshift 1, it moves into a state of becoming high energy. And similarly, it moves from a state, which I thought was quite surprising, from a quiescent galaxy host into a star-forming host. So I don't know if anyone can make sense of that, but that's what the data says. Right, and this is a second approach. So with the first approach, if you're simply maximizing the signal to noise of X-ray and radio, you're going to expect to find a lot of star-forming contaminants. Even if we do subtract the radio and whatnot, we do expect there still to be some sort of contamination. So a different approach we rather thought of was, let's modify the algorithm slightly to select 2 disjoint subsets. One subset maximizes the radio, and the other subset maximizes the X-ray. So we found that so I refer to it as cluster 1 and cluster 2 for radio and X-ray respectively. And we see cluster 1, it's selecting these low stellar mass, low redshift galaxies. And as we go to high redshifts, high stellar masses, there's just no detection or poor statistics. And cluster 2, we see it's rather selecting these high redshift, larger stellar mass galaxies. So that seems to be the main discrepancy in these two populations that we ended up selecting. And if we look at the X-rays, similarly, cluster one is just optimizing radio, so we don't really see any sort of X-ray detection. But cluster 2, which was just optimizing X-ray, we do see some detections in the same bins where it had radio detections, in these large stellar mass, large radio bins. Right, so this is where it becomes quite interesting. So cluster 1 is that tan color. I actually can't even make out. Yeah, Nathan's going to call it that tan color. So cluster 1, you see very high percentage of starbursts, while cluster 2 seems to be this quiescent population that seems to have been driven off the main sequence from high redshift to low redshift. And that black dotted line you'll see in the lower plot, this is a interesting line. It was used by Ito et al. To classify quiescent galaxies. So you see it's quite interesting that our sample seems to almost consistently lie on this quiescent galaxy classifying line. Once again, we look at the radio excess emission, and we find that there's a general trend in this cluster 2 population where the fraction of AGN over total luminosity seems to actually increase from this very low fraction up until redshift 0.5. And once again, if we just look at the fundamental plan of black hole activity, it's not as clear as in the previous plot if there's a transition from a high energy state to a low energy state. So I think that's where it comes in, where we can't really use these Herg and Lurg definitions to really make sense of what's going on in these radio quiet AGN. And as a summary, introduced a really cool algorithm. This is just a first approach that we'd come up with selecting AGN. And hopefully we can use this in tandem with other approaches to potentially make more sense of radio quiet AGN. Cool, thank you.
Okay, we have time for one question. Aaron, there?
Thanks for that. Aaron Redbotham at IAU. Interesting talk. Just wondering, you showed star formation rate or specific star formation rate plots quite a lot. Do you know what is causing that discretization effect, the streaking?
You mean the separation of these two populations in the bottom plot or top plot?
No, just the streaking in general. You can see there's all these.
Oh, that's just from the SED fitting in Cosmos, yeah.
But I mean, I do a lot of SED fitting. That's not necessarily common to SED fitting. So what's going on there? I mean, it doesn't have to look like that.
If you just take all galaxies in the Cosmos catalog and plot them, that's generally the trend you see. That's nothing from my part. I think that's just the Cosmos. Yeah.
Okay, I need to speak to some Cosmos people maybe. All right, thanks.
I don't know, this is my guess from your comment that if you had very low star formation rates or if your model is converging at low star formation rates, could that be just maybe poor fits? Low signal to noise? Oh, okay. All right, that's odd.
Yeah, it's a feature actually in the catalog. We have seen it a lot. I think there is a problem in the modeling. Anyway, thank you very much. The next speaker is Kijin Zhu. Is it here or online? It's online? Ah, okay. Sorry. Okay, so can we get him online? Ah, it's a video. Sorry about that. Okay, so if you can play the video.
Everyone.
some specific light ratios as indicated by the photon model. They are also directly sensitive to gas metallicity, as shown in the middle plot. That if we know the specific light ratio, the value of a certain light ratio, for example, here showing N2H alpha, if we know if we measure the value of N2H alpha light ratios, we can directly interpret the corresponding gas metallicity in the spectrum. This is the power of photon models. And the other thing, instead of in addition to only obtaining the gas metallicity parameters of a spectrum, what else can we learn? Well, if you have an IFU spectrum, which is example shown in the bottom right figure, that we not only have a single spectrum in the building containing the emissions from the galaxy center, that we have a multiple spectrum that's spreading all over the galaxies. And then we plotting, this is called the IFU spectrum. And then we plotting all the spectrum onto one BPT diagrams. So this is the upper right figure is showing you an example of plotting the IFU spectrum of NGC 1068 to the BPT diagrams. And you can see that for this galaxies itself, it forms star formation AGN mixing sequence on the BPT diagrams. This indicates that some certain area in this galaxy are dominated by AGN excitations, and then some certain area in the galaxies are dominated by star forming regions, and then they are mixing in some other regions. So this is showing us the power of IFU spectrum. But this is the case when only star formation AGN presents in the active galaxies. As we mentioned before, shocks can also play their role. So what can we do if shocks also present? Can we separate them on a 2D diagram? Unfortunately, the answer is no. As shown in the top right figures, if we are adding the shocks model, which is the purple one and the black one, to these BPT diagrams or standard optical diagnostic diagrams, you can see that the shocks model grids are mixed up with either the AGN model or star forming H2 models. So even though that we can separate the star formation in H2 and AGNs based on these 2D diagrams, we cannot separate them if shocks also present, and we cannot exclude it that the shocks present in the galaxies. So what can we do in this case? There was one work proposed previously by Joshua D'Agostino, a previous student of Lisa Kivley, that an empirical theory diagram could help. So this is showing how the empirical theory diagram works. The empirical theory diagram uses ER function as one axis and velocity dispersions of a single Gaussian component as the second axis, and the distance of each spaxel toward the galaxy center as the third axis. What is the ER functions? The bottom right figures show you how the ER functions corresponding to the locations of a spaxel along the star formation AGN mixing sequence. So if you're in the pure AGN regions, that your ER functions value close to 1. If you're in the pure star formation regions, then your ER function close to 0. So for this galaxy NGC 1068, when we plot its IFU spectrum on this empirical theory diagram, we can see that they separate into 2 sequences. And then they assign the first sequence to be a star formation AGN mixing sequence and the second sequence to be the star formation shocks mixing sequence. And then calculate the contributions of each mechanism based on the location of data points on these 3 diagrams. By doing this, they can separate the star formation AGN and shocks in these galaxies. This is a successful case. We hope that this empirical 3D diagram stands for all other cases where IFU spectrum was obtained. But unfortunately, the successful rates of the empirical 3D diagrams are only less than 20%. Most of other galaxies, as shown in this plot, they failed in empirical 3D diagrams. As we can see, that it's very hard to tell the two separate sequences on this empirical 3D diagram for these two galaxies. Does it indicate that there's no shocks in these galaxies? Not necessarily. So the empirical 3D diagrams fails in some galaxies. What can we do in this case? This is where my work jumps in. I figured that if the empirical 3D diagrams failed and the 2D diagram cannot solve the problem, then we still need to go for a 3D diagram. But this time, maybe we could use the theoretical models and for helps. So on the right, I'm improving the 3D diagrams to be a theoretically based 3D diagrams. New 3D diagrams are based on the two axes of the new 3D diagram from the BBT diagrams. So here in the new 3D diagrams, I'm using N2H alpha and O3H beta as the two axes, and then adding a third axis as the velocity dispersion, which was used in the empirical 3D diagrams. But then we also add the theoretical models to this plot, to these diagrams. So here, the red dash grid show you the H2 model, the black or gray dash grid showing you the AGN model, and the magenta grid showing you a fast shocks model, and the green grid showing you a slow shocks model. And also, we are overplotting the IFU spectrum of these same galaxies and GC424, which was found in the empirical 3D diagrams. Let's see how it distributes. As this 3D diagram rotates, you can see that there are these backsols. Distribution of the IFU spectrum are mostly divided into three groups. Okay, let's stop here. So one groups are located in the H2 model regions, and one group's located in the AGN model regions. And the other group are mostly in the fast shocks model regions. Besides this, we also see a connection or two sequence linking the star formation region and shocks region, and the AGN region and the fast shocks region, indicating that not only this galaxy not only have a mix of three mechanisms, but they are also somehow mixed together, which are as shown in these 3D diagrams. So I hope this is convincing that the new 3D diagrams is very powerful in not only identifying each mechanisms, but also the mixings of each different mechanisms. And now let's see some typical example of how IFU spectrum of a galaxies distributes on these 3D diagrams. So this is an example of pure star formation AGN mixing, so no shocks in these galaxies. How does the spectrum distribute? So it's basically mostly a flat distributions in the 3D diagrams, only spreading the star formation region, AGN region, and there's no or very little spaxel goes up, which could due to like the uncertainties in the measurements. And this example is the star formation in slow shocks mixing, where we can see that as if we just interpret from the BPT diagrams, you can only see a star formation. It seems to be a star formation AGN mixing sequence, right? But then if we click it or show it, view it in the theoretical 3D diagram, you can see that the parts where you think it goes to AGN's regions are actually closer to the slow shocks model grids. So in this case, it's more likely a star formation and slow shocks mixing rather than a star formation AGN mixing sequence. And the next example is the AGN and fast shocks mixing, where all the spaxel located in an AGN region. It's very easy to identify it as a pure AGN galaxies. But if we plotted it in the new 3D diagram, you can see there's actually a strong branch goes up to the fast shocks model grid, right? So this case is an AGN and fast shocks region mixing rather than a pure AGN's galaxies. And last, we are showing back this NGC 1068 galaxies that we already know they are star formation AGN and fast shock mixing. And how does it look like in the new 3D diagrams? So apparently one group's starting a sequence from spreading the star formation AGN's regions, and there's also a very strong sequence spanning the AGN region and fast shocks model grids regions. So this galaxies is apparently a 3 mechanism mixing galaxies, as the same conclusion from the empirical 3D diagrams. So here shows you that the power of the new 3D diagrams. Due to the time limit, here are my summaries. If you have any questions, feel free to ask. Thank you.
Hi, everyone. I'm online for any questions.
Okay, thank you. Any question for speaker online from the audience or online? There is one here in the audience. If you can say who you are.
Hello, I'm Roberto Cef from Universidad Diego Portales in Chile. So this is incredibly interesting work. I was wondering, have you tried this with some of the other BPT diagrams, or are any of the other line ratios, when you add them to this information, sort of making a higher dimensional space, do they give you more information, or this you get about the same?
Very good question. Thank you. Yeah, I actually explore a lot more line ratio than I show here. But as we all know that the BPT diagrams stand out from all the two other 2D diagram from at least in the optical wavelength. So this one are currently doing the best. But we also aim to try with other wavelengths. So for example, in the near infrared and also in the UV wavelengths. And in these different wavelengths, they did give us some different, like more informations in some diagrams. But in this presentation, I'm only showing the optical work.
Thank you. I think we need to move on, but thank you very much. We have 30 seconds. Online then? Anybody
Yeah,
can
I
speak?
had a quick question. Hi, this is Stephanie Junot from NORLab. I really enjoyed your talk. This is great stuff. I was curious have you tried to see what happens if one has just one fiber per galaxy? Because right now you have the IFU and you have a lot of, you can map the excitation, but what if somebody wants to try to apply this to like SDSS or some other survey that's just one fiber? Like, is there a chance to disentangle these processes?
Yeah, this is also a very, very good point. I think I don't have a very clear answer for this now, but I do have a plan to test it, that if we, for the same galaxies, we can see how the IFU spectrum distribute and then how the single aperture spectrum locates in the 3D diagrams. And maybe this can give us some hint of how we can interpret this for those single aperture spectrum of our galaxies. I hope that helps.
Yeah, I'd be curious to see what you find. Thank you.
Thank you.
Thank you. I can see online there are other questions, but in the interest of time, we need to move on. I'm really sorry. But you can post them on Slack and the conversation can continue. So I invite here last speaker of today, Leon Saponata. Sorry. I'm really sorry. Who is going to talk about high resolution insights into black hole accretion dynamics and jet phenomena. I'll give you 2 minutes warning.
Okay. Hello. Hello, everyone. My name is Leon Salas, and I'm a PhD student from the University of Amsterdam, working on under the supervision of Sarah Markov and Oliver Porth. And today I'm going to present this project about the resolution analysis of magnetically arrested disk simulations and also give an update on the variability crisis of Sagittarius A star. So yeah, for the ones of you that attended the session, the EHC session last week, I hope that you are convinced that for the case of the supermassive black hole, Sagittarius A star and M87, the multi-wavelength observations and also polarization measures strongly suggest that the best models are the so-called magnetically arrested disks. Yeah, and this comes from both linear and circular polarization. And there is also like this, sorry. Oh, okay. So yeah, it's also proven that the shadow size and appearance is consistent with general relativity. So this is important that now we have to do like a more in-depth analysis of these simulations. So here comes like my research project in which I'm analyzing what happens when we increase the resolutions of these simulations. So you can see in this table showing the number of simulations that we analyze going from resolution 1 to 5. And here is showing the number of cells in the radial, polar, and azimuthal directions. Just to give you like an idea more or less, like the resolution that EHC uses in their papers is like between resolution 1 and 2. And it's expected that as we go to extremely high resolution, like there are like signatures of turbulence and also instabilities that become more resolved. So here in these vertical cuts, you can see in the left a plot of density, in the middle a plot of the proton temperature in Kelvin, and on the right a plot of magnetization, in which I'm dividing the system in 3 components. So the so-called jet spine, which is a strongly magnetized relativistic outflow, the jet sheath, which is mildly relativistic outflow, and the disk. So one of the characteristics of these matter states is that the magnetic field is so strong that it can suppress accretion with the formation of a current sheath, as you can see here. And when we go to this extremely high resolution, there are signatures of instabilities. For example, in this current sheath, you can see clearly signatures of tearing instabilities with the formation of plasmoids. And also along this interface between the jet spine and the sheath, there are like some wave-like features that can induce mixing. So yeah, this extremely high resolution, as I mentioned, show these signatures of plasmoids. And this is important because this current sheath is transient, and the energy that can be dissipated, so the magnetic energy dissipated into other forms of energy, like thermal energy or radiation, this can explain very high energy flares, like for example, the near infrared or X-ray flares from Sagittarius A star, or even gamma ray flares from M87. So now if we see an equatorial cut of density, you can also see like these features of expelling these low density cavities, which are in general like extremely high temperature and magnetization. And in this low resolution, these cavities becomes like really diffusive because of numerical resolution. And as we go increasing the numbers of cells, the resolution, there are like real signatures of, for example, these fingers, as you can see here. And if we measure, for example, turbulence, for example, with these viscosity parameters, Reynolds viscosity, that measures the turbulent velocity correlations in the radial and azimuthal directions, there is a clear signature that there is an inward angular momentum transport that is attributed to turbulent convection. So now, again, going to these vertical cuts, here I'm showing the plasma beta, which is the ratio of gas to magnetic pressure. And in resolution 1, you can see like there is more or less like a laminar outflow. And as we go to higher resolution, there is clear signatures of these mixing instabilities that you can see like these wave-like features. Yeah, that is mainly caused that like a shearing motion between these components. So yeah, one of the main results of this analysis is that the jet sheet is not fully converged. Mainly if we see, for example, a plot of the proton temperature, as we go to from low resolution to higher, there is like a clear evidence that the proton temperature increases and also magnetization decreases. And interestingly, if we see, for example, these space time diagrams, we can see that when there is an increase, for example, in the enthalpy, that is correlated with a decrease in magnetization. And that could potentially explain like some features from observation, like for example, these filamentary structures in jets. So yeah, now switching to a different problem, this variability crisis. There is like one caveat of the EHC observation is that when the 230 gigahertz variability constraint is included, none of the models can survive. So all the models are ruled out. So in this project, we are trying to analyze what happens when we not only evolve the ion temperature, but we also include an equation to evolve the electron temperature and see whether it can help in reconciliate simulations with observations. So the way to implement these two temperature treatments in GRMSD is by the inclusion of this equation that includes the electron, the temperature, number density, and entropy of the electrons. And we include like 3 terms here. So the first one is a mimic of heating in magnetic reconnection, in which this delta E is the fraction of electron to overall heating ratio that comes from particle in cell simulations. The second term is just the Coulomb coupling between the species, so between electrons and ions. And the last term is the radiative cooling of electrons. So here we are including synchrotron emission, Bremsstrahlung, and inverse Compton. And also important here to mention is that we are evolving the gas, including a variable adiabatic index. So in general, you can see like here on the left, the electrons are in the relativistic regime. So the adiabatic index close to 4/3. The protons or ions are in the non-relativistic regime. So adiabatic index equal to 5/3. And in general, the mixture of these two species can have different adiabatic index values. So here are the results when we do the radiative transfer calculations. Here you can see, for example, in this shaded area, this is the observations of Sagittarius A star in this with these references. So the magenta dotted distribution here is the prediction from the traditional single temperature simulation, so the simulation that EHC uses. And we are proving here that when we include additional physics, for example, when we include the two temperature treatment, the variable adiabatic index in this red line, the distribution of this modulation index shifts to lower variability values. And when we additionally include cooling, this reduction in variability is improved. Oh yes, and also to mention that the way to measure variability is using this modulation index, M3, which is defined as the standard deviation over the mean in time fragments of 3 hours. And here you can see like a summary of all the simulation that we perform, in which we can see like one level of physics added. And in the end, like the effective reduction in variability is like a factor of 2. And this is something to be expected because in the traditional prescription used by the EHC, the electron temperature fluctuates as much as the ion temperature. But in these two temperature treatments, when we have different adiabatic index for electrons and ions, it is expected that the electron temperature fluctuates less than the ion temperature. For example, that you can see in this very simple calculation. So yeah, going to the conclusions from the resolution study, we see that high resolution revealed these signs of inward angular momentum transport. And this is like a clear signature that turbulence is not fully converged, not even at the highest resolutions. Yeah, and more importantly, like we see like this difference in the jet sheath, that we see like an increase in temperature, reduction in magnetization, and also greater variability. And that could have an impact in the images and polarizations in AGN jets. And also important to mention here and to connect to the first talk of this session is that with these simulations, we can perform like a full GR treatment up to subparsec scales. And those could be used, for example, for to the other kind of simulations, for example, the Pluto large scale simulations as a kind of subgrid model for those. Yeah, and finally, going to the conclusion of this variability project, we have proved that this inclusion of the two temperature treatment, variable adiabatic index, and cooling reduce the light curve variability, not only at 230 gigahertz, but also in these other frequencies. Yeah, but however, the historical observations still show a lower variability than the simulations. Yeah, and finally, like even for the low accretion rate of Sagittarius A star, we have shown that radiative cooling still affects the accretion flow, like lowering the electron temperature in the inner disk, reducing the synchrotron flux at an average of 10%, and also shifting the modulation in the distribution towards lower variability values. And as you can see, like in this plot, for example, in the left, showing like the results of the time average when we include cooling, and on the right when cooling is not included. Yeah, and that's everything. Thank you.
Question from the audience or online? There's one over there. We lost the volunteers. There is one there. Thank you. Sorry for mispronouncing.
Thank you for an awesome talk. I guess I have one very specific question about these wave patterns that you're seeing in the jet. And I'm sorry if I missed this. Do you have any gut instinct on whether these form a roughly stable power spectrum, like a spatial power spectrum? And do you know if that's directly tied to the turbulent power spectrum? Because it would be nice to know what kinds of spatial scales to expect for variation in the jet and larger scales, and see if that actually unwinds and propagates in a straightforward way.
Yeah, this is something that we didn't do here, but yeah, we didn't calculate like the spectrum here of turbulence. But what we are showing here is that when we go to higher resolution, we are seeing like a higher variability in all the properties of the jet sheath, in temperature and also magnetization. Yeah, and that could have like an impact, for example, in the observations. For example, because these wave-like features kind of change the structure of magnetic field, and that could have an impact not only in total intensity, but in polarization.
Great. The other thing that comes to mind is that having some prediction for small scale structure in the jet could tell you how to interpret, really high amplitudes in VLBI studies of blazars. Are these coming from compact knots? Are they coming from just diffuse turbulent structure? I think it could be quite important. Thank you.
Yeah, thanks.
Okay, I don't see any other hands in the room. Online, is there anything? Okay. If not, we are done for today. Thanks again, Leon, and thanks all the speakers of this morning session for being on time and allow us to now go to the Young Astronomer Lunch. If you sign up, please go there. They seem oversubscribed, so make your way over there. And I'll see you this afternoon in the continuation of this session. Thank you very much.
Okay, thank you.
Good afternoon. Apologies for the delay. We are looking for Elena Nokrina. Are you here? Please come to the front. And we're also looking for Georges Philippos. He's online. Georges Philippos. Okay, we'll check the Zoom room. Okay.
So we are a few minutes late. So the first person to speak will be Eckhard Sturm.
Test, test. Aufwasche. Okay. Okay, cool. Okay, good afternoon, everybody, and to the organizers, many thanks for the opportunity to present some recent results from our ongoing program of spatially resolved studies of the innermost regions of AGNs with ESOs, VLTI interferometer, and Gravity Plus. So the method of choice here is spectroastrometry from interferometry in the near infrared. And my main message today is simply that with this method, indeed, we can spatially resolve the broadline region and the innermost regions of AGN near and also in the high redshift universe. Now that, of course, with resolution of in the micro arcsecond range. So that, of course, opens up a completely new toolbox for spatial resolved studies of AGNs, a fantastic playground, if you wish. And today I can only concentrate on two small aspects of the many things you can do because of the time. And number one is, of course, so if you resolve spatially the borderline region, then this gives you information about the size, the structure, the kinematics of the BLR, again, from direct measurements. And so some of the long-term goals of our programs are to provide a new basis for understanding of the BLR physics. And number two is also at the same time, with the same measurements, we can very accurately determine the black hole masses of the AGN. And again, in locally, but also at high redshifts. So with all that together, we can derive our own independent versions of AGN scaling relations, and I will show you what we find and why that's important. And all together, then this shall, of course, advance our understanding of the evolution of black holes and the co-evolution with the host galaxy over cosmic time. As I said, there's many other super interesting aspects, things to do, which I cannot cover today. Now, so interferometry, that means we measure interferometric patterns, fringes, but for the purpose of this talk today, maybe the only thing you need to understand is that for the spectroastrometry method, we make use of the phases, because these phases tell us something about the on-sky position of the components of a structure on sky. Okay, and if that structure happens to be, say, a rotating system, like, say, broadline clouds, broadline region clouds in rotation around a central supermassive black hole and its gravitational potential, then this phase signal as function of wavelength, yeah, it doesn't matter, as function of wavelength or velocity has this characteristic S shape here. And that is because for the corresponding line, a broad emission line profile, the various blue shifted and red shifted parts are coming from different positions on sky. They have different photocenters, and that's how you get this S-shaped phase signal. Okay, for a real object like the famous quasar 3C273 with this nice little radio jet coming out, I'll show you how this looks like in real life. So this is again the picture, and this is what we measure. At redshift 0.2 in the K-band, it's the Paschen alpha line, and you see the spectral line here, and you see the phase signal here. And this looks exactly like this textbook example for a rotating system. And the corresponding photocenters of the broadline region that we derive from this as function of wavelength or in color velocity is indeed this velocity gradient across the BLR and perpendicular to the radio jet. So that's a beautiful example of the rotating BLR system. Now you can read off the radius of the BLR directly. It's a direct measurement, no modeling involved, nothing. It's just interferometry, and you get out maybe 30 micro-arc seconds. So we are in the micro-arc second regime. And with the width of that line, you can then also derive a mass of the black hole. But these photocenter radii are a little bit underestimated because we have to do some spectral, in the spectral channel, some binning because of signal to noise issues. And also the inclination, of course, has a little bit of a role. So we can learn a bit more about the system if we now go ahead and do some modeling, and we do some sort of straightforward, forward modeling approach with a system of several 100,000 clouds that rotate, and the parameters for the fit then simply are the mass of the black hole, the opening angle of the disk, and then you have a radial and angular density profile and some orientation on sky. And we fit then the line profile and the phases simultaneously, and the fit result here in this case is this magenta lines that you see here, so an excellent fit. And from this then we get a better radius and a very accurate supermassive black hole mass. So this is a point sub-parsec structure at a distance of 700 megaparsecs, and that's the strength of this method. We have done this now for 7 objects, and they are listed here in this table in the nearby universe. You see some fit results, radii, masses, and so on. And this is already kind of summary of the first part of my talk. Again, so we measure photocenters, that's a direct measurement. We resolve the BLR. We measure significant velocity gradients. We read off sizes, and then we do a modeling and get all kinds of geometry of the BLR and radius and masses. And indeed, most of the AGNs that we have studied so far can be well described by a thick rotating disk of clouds. Some do show some significant contribution from outflows. In this case, you also see that then the phase signal looks a little bit different from this S shape. But that's what we could do at this point in time. We will get many more objects in the not too far future, I hope. What we also want to do is then to put the findings from gravity in the context of AGN scaling relations, like the radius luminosity relation that you see here. So that's a relation between the radius of the broadline region and the luminosity of the AGN, which has been established in the literature before and which is the basis of all these methods, single epoch methods, with which we derive currently masses of supermassive black holes at high redshifts as well, for instance, with James Webb. But they have been locally derived with a number of assumptions, and nobody knows if they still hold at high redshift and if there's other parameters that play a role. So what you see here is now, to my knowledge, the first RL relation that has not been derived with reverberation mapping. And admittedly, it's just 7 objects so far, but we scan or cover at least already quite some luminosity range. And what you see is that, so the dashed line is the canonical value from the literature where the radius is proportional to the square root of the luminosity, so an exponent of 0.5. But if we fit our data, we find more an exponent of 0.4, a flatter relation. And if you then look, the 2 objects that deviate most from this dashed line here are the most luminous objects that we have, and they are also very highly accreting objects. And indeed, from reverberation mapping in the recent past, it is known that highly accreting objects show lower radii of the BLR. So you have there an undermassive black hole, which is trying to catch up, so to speak, with high accretion rate, and this combination then makes the radius of the BLR smaller. It could also be that the proxy for the bolometric luminosity, monochromatic luminosities that we use in the X-ray, or in this case, the 5,100 angstrom luminosity, that we just using them wrong. There is indications that the bolometric correction should be nonlinear because it depends on the luminosity. That means the ratio between UV and optical in this case, the SCD changes with luminosity. And there is recipes in the literature for such corrections, and if we apply them, we can recover an alpha equals 0.5 relation. But so with larger samples, we should be able to shed more light on this as well. Okay, this was all in the local universe. We can do the very same kind of analysis also at higher redshift, like at redshift 0.2, where the cosmic evolution of star forming and black holes peaks. And that is due to an upgrade of gravity to gravity plus that's ongoing. It's an upgrade of the entire VLTI infrastructure, but it's supposed to be finished by 2026 when all 4 UTs will have their own lasers. And then we will be able not only to measure the handful of objects in this corner, but thousands of AGN out to very high redshifts, maybe even redshift 7. And this is the first example where we did this, a quasar at redshift 2. So the quasar is up here, but the fringe tracking object is here. I have no time to explain this, but this is one of the advantages of gravity plus. And we do the same thing. We measure an H alpha line, we measure a phase signal, we read our photocenters, we model the thing, and then we get a radius and a mass. Turns out, and that in 3.5 hours of integration time only at redshift 2. And it turns out it's a highly accreting object again, and again, its radius is smaller than what you would expect. So to summarize this, I have shown you 7 local AGNs where we find this little bit flatter slope, reasons yet to be understood. But we are also now beginning to do the same thing at redshift 2 for the moment. We have observed 5 QSOs to date. And if I put them here on the same relation, you see the blue objects and the red objects here. And if you then look at the black hole masses that we derive with gravity and the black hole masses that you would get with the single epoch methods based on reverberation mapping, there is quite some difference. So you would overestimate your black hole masses if you blindly apply this method at high redshift for James Webb redshift 6 or redshift 10 objects by maybe up to an order of magnitude if you don't take into account these effects that we are beginning to see here. Okay, that's my last summary slide. So gravity is really breaking new grounds in interferometry. We resolve the broadline region at low and high redshifts. I've shown you 7 such measurements in the local universe. From this, we get the BLR geometry, BLR kinematics, black hole masses, scaling relations. The same thing now at high redshift. And then we can really get our own scaling relations, test the existing ones, if there's an evolution with redshift, if there's other parameters that need to be taken into account. That's it.
Thank you. Thank you for a great talk. I was wondering, have you tried it on the same object with several different emission lines of different ionization states? And do you recover the reverberation case where the high ionization lines tend to be smaller and the low ionizations further out?
Not directly. I mean, we have to live with whatever is in the K band. Extension to other bands, of course, would be great in the future, but we have indirectly tried to, and the person who did this actually happens to be in the audience here, Lukas Kuhn. Inspired by the method we are using, we have tried to come up with a single epoch method, which makes use of several lines from extruder or what have you, other galaxies, where you can then indeed study how different lines, different sizes, different time lags, as it's known from aberration mapping, and how to interpret this and to put this all together. So indirectly we can do it. Directly we have to see what's in the K band. Yeah.
Thank you.
Sorry, Jose, maybe I missed it. You said that you measured some inflows and outflows in the local.
Yeah.
What about the velocities? Are they comparable with what measuring the AGNs using the red tails of the other lines? What are the velocities that you measure?
Oh, so yes. First of all, at this point in time, we should not overinterpret these modeling results because it's not a very physical model of the outflows, but it's more like very elliptical orbits that are modeled, and then you have some extinction in the midplane, and the middle the model can then distinguish outflows from orbital from radial motion. Velocities that I cannot tell out of the top of my head. I actually would have to look this up. Yeah, but this is the hope for the future. We want to put a bit more physics or discrete model put into our kind of modeling, for instance, and really then get a grasp of how a wind and then an outflow is launched from that broadline and accretion disk region. That's one of the long-term goals, indeed. Yeah.
Good afternoon to everybody. First of all, I want to thank the organizers for giving me an opportunity to participate in this meeting. My talk will be dedicated to the core shift and how the jet collimation profile and jet acceleration affect the measure of this core shift. What can we explain, and what can we derive from our modeling? So here, just to remind you what the core shift is, here is a nice cartoon from the paper by Hade et al. 2011. Here we have the central source, black hole, and to the right, the jet is expanding. And so the physical values, magnetic field and emitting plasma number density, which define the local jet opacity, are also changing. And we see that for each given frequency, we see eventually the surface with an optical depth approximately equal to unity. We see it as a bright stationary feature, which we call a radio jet. And the higher the frequency, the closer to the black hole we can look at. The distance of the observed radio core from the central source is a power law of the observational frequency. And for some time, I will talk about this KR, which is Kerr shift exponent. So there are quite a lot of very nice multi-frequency observations which confirm this value KR is close to unity. Here, just one example of a sample of dozen of sources, and here is M87. So this value can be easily explained with quite a simple jet model. So if we have a conical jet, if the bulk plasma motion Lorentz factor does not depend on the distance along a jet, and if we assume the Blanford-Koenig scalings for emitting plasma number density n and magnetic field B in the plasma proper frame as a function of a distance along a jet r, we will obtain this power law with KR equal to unity. However, recent observations showed that probably these assumptions do not hold. For example, jets closer to the central source may deviate from the conical shape and collimate rather like a parabola. And usually this region covers the distance at which we observe cores at the typical frequencies 8, 15, 22 gigahertz. So the typical frequencies for core shift measurements. So jets are not conical probably. And also, I will not go into details, but numerical and analytical modeling suggests us that if plasma in a jet is effectively accelerating along a jet, then a jet attains a quasi-parabolic shape. And further, when the plasma attains almost constant Lorentz factor, which does not depend anymore on the distance on a jet anymore, its boundary attains a conical shape. And there are even some observational hints on that. Here is the jet collimation transition point, the Lorentz factor. Here we see effective acceleration, and then it ceases and velocity even drop. So probably we should consider accelerating jets. Which is more, there are actual observations where KR, the core shift exponent, deviates from the unity. Here, just to remind you, M87, it is close to unity, but this curve in NGC 315 is consistent with KR 0.56, and in this walk, KR is equal to 0.78. So I will try to explain them. I will regard the jets of arbitrary shape. Here, D is a jet width, R is a distance along a jet, and K is an exponent which defines the jet shape. If K is equal to 1, then we have a conical jet. And if the K is equal to 0.5, it's a strict parabola. Then we can regard both constant bulk Lorentz factor or extreme case of effectively accelerating plasma Lorentz factor, gamma proportional to jet width. The last fact affects the classical Blanford-Koenig scalings, and the result is as follows. If the jet is not accelerating, plasma attained its final velocity, then core shift exponent is equal to 1. For con, it's unity, which was previously observed and anticipated, but for parabola, it's 0.5. However, if we look at the accelerating jets, then the result for core shift exponent depends on the viewing angle. If the viewing angle is small enough so that our line of sight is always at each distance is inside an emission cone, then Doppler factor changes along a jet, and KR is equal to 4K/3. So for a strict parabola, it's two-thirds. I'm sorry. And if we observe a jet at a large observational angle, we probably see only the junks of plasma at the critical angle, and we can assume that Doppler factor is constant. And in this case, KR, core shift exponent, is equal to 2K. So it's 1 for a strict parabola. And now let's look at the particular sources. The first source is M87. We know that they're observed at every frequency, reasonable frequency, radio cores lie well inside the parabolic region. So here I left only this one. And these are observed parameters, exponent which defines the jet shape, and observed core shift exponent. And we probe different plasma acceleration scenarios. And the preferable one is that plasma is still effectively accelerating here, but the viewing angle is large enough so we can assume this equality. And this actually what is observed. For NGC 315, the situation is more complicated and more rich. So we have here a parabolic domain, presumably accelerating conical domain, and the cores at high frequencies lies in the parabolic domain, and cores at lower frequencies lie in conical domain. So we probe two cases. Here are the observations, which we try to fit with our different acceleration scenarios, and the preferable solutions are highlighted here in blue. So for a parabolic flow, the jet must be accelerating, but viewed at a smaller angle than is usually derived for this source. And for conical case, the Lorentz factor must be constant. So just as an intermediate conclusion, there are quite a lot of sources now where KR its value departs from the unity, and it falls mostly exactly in the domain of 0.6, 0.8, which we actually can explain within the model of parabolic accelerating part of the jet. So what can we derive from this? Let's look at the core shift coefficient, omega R nu. It's from the one hand, it's an observed value because here is the core shift and just two frequencies at which we measure the positions of this core. But on the other hand, core shift coefficient is a function of a local magnetic field B and emitting plasma number density N in a plasma proper frame. So in order to assess B and N, we need to set some relation between them. The classical result is that we assume equipartition. The energy density of emitting plasma is equal to energy density of magnetic field in a plasma proper frame. And which is more, this relation actually holds along the jet if it's conical and non-accelerating. However, if the jet does accelerate, then this relation cannot hold at any distance, and we need to assume something else. And in this work, we assumed that the core shift coefficient being constant, at least separately in parabolic and conical domains. And this is supported by measurements. Here is the core shift coefficient, and here pairs of frequencies, and total number of frequencies in these observations was 6. So it does look like a constant. So if we assume this, then we have the whole class of relations between N and B. And the simplest one looks like this. And it has a very clear physical meaning. The ratio of emitting plasma density to total plasma density in a jet stays constant, does not depend on the distance along a jet. So, assuming this, we can rederive the expression for B and obtain the magnetic field at 1 parsec scale. And which is more, we also can easily, I will not go into details, we can easily extrapolate it down to the gravitational radius scales. Here are the results. The sample are the sources with a confirmed parabolic shape. And for M87 and NGC 315, they are confirmed by independent measurements. And just a few words here, a few quick words. This core-shift coefficient may assume different values in parabolic and conical domains. We can find magnetic field from 2 branches. And here how we find it and recalculated it into a core frame. And here are my conclusions. Thank you very much for your attention. Thank you.
Please ask the question online, Catherine.
Hi,
Catherine.
thank you. Nice talk. Thank you very much for the presentation. I have actually 2 questions. One is, how do you deal with jets that have no parabolic or conical expansion? So there are a handful of sources that show, for example, more cylindrical collimation, for example, 3C84 at some point, or NGC 1052. How does this fit into your model? And the other question would be that we know that the measurements of core shift are biased towards the resolution of the telescopes and the activity of the AGN jet, so that the core shift, the core might shift not depending on the frequency but on the observation conditions. So how do you account for both of these uncertainties?
Oh, okay. So if I understood your question right, we took arbitrary jet shapes. So we do not describe only parabola and cone. And in fact, in the case of NGC 315, that's the case. So, and we also in the paper we have more general expressions. So you can put any jet shape and any, for example, exponent of emitting plasma energy distribution. So we thought about that, but about bias in measuring core shift depending on the conditions. No, it's not there. It's just we have an arrow derived by finding core shift coefficient for single measurements. But no, in this work, we haven't accounted for the probable core shift bias, and we probably should do it.
Okay, thank you.
Thank you. Thank you.
Any more questions? that I can see. It's okay, so the next speaker is Randy Chavez.
Okay, let's work. Okay, let's work. Okay. Hi, everyone. My name is Randy Chavez. I'm a graduate student at Harvard University, and today I'm here to tell you about the work that I've done on determining the prospects of detecting the jet in Sagittarius A star with VLBI. So, as I'm sure you all know, we have a 4 million solar mass supermassive black hole at the center of the Milky Way galaxy, Sagittarius A star, or Sag A star for short. So, with the title of this talk, I'm promising you some sort of in Sag A star. But as of right now, there has been no, a jet coming out of Sag A star has never been conclusively observed. So, before I get into the work of my project, I wanted to first motivate why we might expect Sag A star to have a jet at all. So for this, I think it's really useful to think about jet launching mechanisms. And so as it turns out, if you have a rotating black hole in a magnetized accretion flow that has strong and ordered magnetic fields, you can actually launch a relativistic jet, which is powered by the extraction of spin energy from that central black hole. And this is known as the Blandford-Snag mechanism. So one of the key requirements of this is the presence of these strong and ordered magnetic fields, which is something that we can probe in both M87 and Sagittarius A star with the EHT in polarization. So with the first polarized image of M87 from the EHT, we saw that on event horizon scales, it does have these strong and ordered magnetic fields. And as is well known and well established, even mentioned in the previous talk, M87 has a bright, powerful, booming relativistic jet. But even more interestingly, when you apply the same logic to Sag A star, on event horizon scales, it has an almost identical magnetic field structure. It has these strong ordered magnetic fields. So by this logic, I think this is really strong indication that it might have a relativistic jet. And as it turns out, the simulations agree. So the GRMHT simulations by the EHT that are most favored by the EHT data do have a jet component present, but as I mentioned earlier, it's never been observed before. So the questions I wanted to answer with my talk are, one, why haven't we observed a jet yet if it's there? And two, what's the best approach to image this jet with future observations? So let's take a look at that GRMHD model. So this is that GRMHD simulation ray traced at 4 different observing frequencies, 86, 115, 230, and 345 gigahertz. These were chosen because they are targeted by either current or next generation VLBI arrays. And just to build some intuition for this jet, so it is quite small and quite faint. These image field of views correspond to about 5 by 5 AU in physical scale, so it's pretty small. And also it is very faint. So at 86 gigahertz, where the jet appears strongest, it's contributing about 10% of the total flux, so not too bad. But as you move to higher and higher observing frequencies, the jet becomes more optically thin, it becomes a lot fainter, and by 345, it's only contributing about 1% of the total flux. And this will become relevant later. But just some other details about this jet model, it has an unconstrained position angle, so it can point in any direction along the sky, and this will become relevant later. Okay, so we have this faint, weak jet. What does that mean? Well, it actually could be hidden by the effect of interstellar scattering. So between us and the galactic center, there is turbulent ionized plasma in the ISM that scatters light at millimeter wavelengths. And the degree of scattering, like the severity, scales with observing wavelengths squared. So, and it's also a bit more extended in the east-west direction when compared to the north-south. And so this figure that I'm showing you here on the right is just showing how the effects of scattering affect the appearance of the jet. And the main takeaway from this plot is that as you move to higher and higher observing frequencies, the scattering is reduced because of this lambda squared dependence. But because the jet is becoming more optically thin, it's actually becoming much harder to observe it. And therefore, the capabilities of the specific array you're considering will actually have a very strong dependence on whether or not you could actually detect this jet. So let's look at some actual real arrays. So the arrays that I considered in this project are two currently operating arrays, a GMVA used with ALMA, the EHT, and two next generation VLBI arrays, which are the NGEHT and the NGVLA. And here on the left, I'm just showing you the different frequency and array combinations I considered. So as you can see, these three arrays are quite different from each other. They have different frequency capabilities, they have different configurations, different sensitivities. So how can we compare these all against each other? So for my non-VLBI people in the room, I just wanted to give you some intuition. So in VLBI, we make observations with pairs of telescopes, and each pair of telescopes forms a singular baseline. And to quantify this, we can form what's called the UV plane. Oh shoot, this was supposed to be, oh no, it is an animation. Beautiful, okay. So we can form what's called the UV plane, which you can quantify those directions and distances. And the intuition to have is that each baseline in your array detects scales and structure on your on-sky image of theta is equal to lambda over d, where lambda is your observing wavelength and d is your baseline distance. So if you have very long baselines, you're going to detect very fine structures, which is ideal if you want to see something like, say, the black hole shadow. But if you want to see, say, a larger jet, you actually want smaller baselines. And with that intuition, let's look at this plot here. Here, I've taken all of the arrays that I showed you in one of the previous slides and plotted the UV coverages colored by their sensitivities. And so what we want for jet detection is actually high sensitivity baselines in this gray shaded region. This is the region associated with that extended diffuse faint jet emission. And looking at this plot, you can see why current VLBI hasn't been able to do this. So the currently available arrays of GMVA at 86 and the EHT at 230, both either don't have very many baselines in this region, or the ones that are present don't really have sufficiently high sensitivity to get that diffuse jet emission. But as you move to next generation VLBI, suddenly you really start to fill in that gray shaded region, especially at 86 and 115, which shows that next generation VLBI is going to have great potential for this task. So I'm not really going to get into details on this, but the next step for this project was to actually create images. The only detail you really need to know is that I used an imaging algorithm called COMRAD, which is frequently used or well established in the EHT, which takes a Bayesian approach to imaging, which just means that all the uncertainties due to, say, sparse data and instrumental corruptions are taken into account in this imaging process. So, okay, with that out of the way, let's look at some images. So I first started at 86 gigahertz. This is what I'm considering to be the on-sky image here. And actually, to make this, I had to make a choice, because what I mentioned earlier is that the position angle is unconstrained. So here I'm considering where the jet is oriented in the north-south direction, aka the direction where it's least obscured by interstellar scattering. This is, you could say, the best case scenario for the jet orientation. So here are the images that I got. And of these images, it may not be immediately clear what we're calling a jet detection or not. So in order to do this, I fit 2D Gaussians to the top row of images. So not to the data, but the actual images. And then I calculated a residual image just by subtracting these two rows from each other. And what I'm calling a jet detection is the presence of this extended flux in the upper region of the residual image that can only be due to this extended jet. So as you can see, the current VLBI of GMVA is not able to capture that extended emission properly. It can't constrain it, it doesn't detect it. But next generation VLBI does, which is really exciting. In all of these, you can see that little blob on the top. We also repeated the test with a different jet orientation. So now we considered the case in which it's oriented along the scattering. This is, say, the worst case scenario where it's maximally obscured. But even in this harder scenario, same results. With the current VLBI, we're still not able to detect it, which is as expected. But next generation VLBI, even in this harder case, is able to capture the extended emission, which is due to the jet. And in this case, I'm looking for these like little Mickey Mouse ears that are due to jet emission. and say, okay, that was my result at 86. Now let's look at other guys, other frequencies at 115 and 230. So 115 is actually really interesting because at this frequency, you're kind of in a sweet spot. So by going to a slightly higher observing frequency, the effects of scattering are dramatically reduced due to that lambda squared scaling I mentioned earlier. In addition, at this frequency, the jet is still relatively bright, so there's still good potential to recover that jet emission. As you can see, the NG-VLA is just doing a fantastic job here at getting that jet structure. So 115 is really exciting. However, going to 230, which is what's targeted by the current EHT, we've just gone too far. So at this point, the jet is just way too faint to be detected by either the current or the next generation EHT. Thank you. And yeah, so although the NGHT performs much better than the current EHT, it's not enough to capture the jet. But yeah, I don't know. 115 is looking great though. Yeah, and just to really confirm our results and making sure that our imaging algorithm is not producing fake jets, we performed a no jet test. So here's an alternative GRMHD model of Psi star that doesn't have a jet. We scattered it. We produced image reconstructions. And lo and behold, all of our next generation VLBI arrays successfully do not produce a jet, and therefore they can tell the difference between these two models, which is really exciting. So yeah, that's pretty much my project. The main takeaways, the lack of jet detection with current VLBI is expected. Next generation VLBI arrays at 86 and 115 currently offer the best prospects for jet detection. And of all the experiments that I considered, the soonest possible one would be with the NGHT and the GMVA used in tandem at 86 gigahertz. So yeah, thank you for listening, and I'll take questions.
Thank you. Great talk, great work. I'm just curious, I'm not familiar with the EHT receivers and such, but have you tried to do these simulations using lower frequencies, maybe L band or C band or something?
Yeah, so I think it's best to, I agree that with most other sources, this will be a fantastic idea. It's just that Sagitt Star is just not the best to work with for this because of this issue of interstellar scattering. So it turns out that like 86 gigahertz in terms of observations is one of the lowest frequencies that we can go to where you can still resolve the intrinsic structure without scattering just completely blowing everything out. So if you go that low, scattering will just obscure everything. You won't see the intrinsic structure.
Thanks.
Thank you. Yep, cool. Thank you very much. So this is not particularly my area, so I just wanted to confirm what you meant by the jet inclination. Is that like kind of more in our line of sight, that angle? Because you said then the PA was unconstrained and I got confused.
Yeah. So what I mean, I agree that it can be confusing. So if this is the jet, this is the inclination, and this is the position angle.
Perfect. Thank you.
Yeah.
Thank you very much.
Yeah, thank you very much. Nice talk, and I think it looks really promising. I'm just curious if you are planning to take into account variability, because of course for Sagittarius A star we see these hour-long flares, a few flares per day, so that should somehow propagate into jet variability and also maybe observability of such a jet, and also potentially if the flow would be somehow precessing, if of course we may expect also jet precession. So if somehow you are studying these effects as well, or potentially are you planning to consider them?
Yeah, so I completely agree with what you mentioned on variability. I mean, it's really clear in this simulation right here, like the time scale here, this is like seconds and hours. Like Sagitt Star is really variable, which makes it extremely difficult to observe, even with EHT. So we did not take variability into the imaging reconstructions, but it's just going to make everything harder. So just in terms of determining an observing strategy, like with this not considering variability, the fact that we couldn't get it at 230 or 345 means that with variability, like it's just not going to happen, most likely. So I think in terms of just coming up with a strategy of what's best to try, I think this still holds because variability is less severe at these lower frequencies. And so you're going to get less impacted by it. So even though like if you include variability, it's going to make it harder, I still think that next generation VLBI at these two frequencies will be the best chance.
ये देवदास
Hello. Good afternoon, everybody. I'm Soumyadeep Das. I'm a final year PhD student at the University of Hertfordshire, and today I'm here to talk to you about how we use SED fitting to classify the faint radio galaxies in one of the LOFAR 2-meter sky survey deep fields. This paper is published in Munros, and it was supported by this lovely bunch of people. After thanking the organizers for giving me a chance to speak, I'll proceed. Yes, there it is. Right. So the radio source population is a homogeneous mixture of star-forming galaxies, radio-quiet AGN, radio-loud AGN, which can be further classified into the efficiently accreting high-excitation radio galaxies, or the HARGs, and the inefficiently accreting low-excitation radio galaxies, or the LERGs. How do we classify these galaxies? Historically, several methods have been used to classify radio galaxies, such as putting a radioluminosity curve or using spectroscopy. Now, when it comes to classifying galaxies, spectroscopy is believed to be the gold standard. And for the LOFAR deep fields, when Weave LOFAR comes online, we'll have complete spectroscopic coverage over these deep fields. But that is in the future. Weave LOFAR is still not here. So in present, how do we classify sources without spectroscopy? One of the potential answers is combining multi-wavelength coverage with radio data. This has been tried and tested over the years, works such as Smolchich and all, Wittem et al., etc. And LOTS is particularly suited for this. So LOTS is the LOFAR 2-meter sky survey. It is one of the deep radio surveys run by LOFAR in the Northern Hemisphere. It is centered at 150 megahertz, and one of the it has several deep fields where it takes repeated observations. One of them is the LASN1 deep field. So we chose this field because it has the deepest radio observations reaching up to 30 depths of RMS 30 microjansky per beam, and it has excellent UV to far infrared coverage. Now, Best et al. 2023, they used similar techniques to classify more than 80,000 radio-detected sources in all the LOFAR deep fields. They used 4 different SED fitters, backpipes, MACFIS, Segal, and AGN fitter. And then they classified the sources into HARGs, LERGs, radio-quiet AGN, and star-forming galaxies. Now, it is a fact that SED fitting is extremely complicated. It is very time-consuming. It is resource-heavy, and it has a very high learning curve. So, how do we avoid using multiple SED fitters to do this kind of classification? We tried to answer this question with one SED fitter, Prospector. So Prospector has several key features that are of interest. It can use extremely flexible non-parametric star formation histories, something like this. It is able to model the contribution of AGN to the SED, so something like this. And it can also account for nebular emission, the emission lines. It also matches the UV and the far infrared emission through energy balance. It also uses dynamic nested sampling to more efficiently explore the parameter space. And last but not the least, it can deal with photometry and spectra, which will be extremely important in the present stage of our study. So moving on, classifying galaxies using Prospector. It's a 3-step process. First, identify sources that are hosting radiative mode AGN. Second, identify sources with excess radio emission. Third, collapse them into a robust classification scheme. So step 1, how do we identify radiative mode AGN? So for this, we answer two questions. Does the source have a mid-infrared excess, and how much of that is due to AGN? So the Nenkova models used in Prospector contain a parameter called the AGN fraction. AGN fraction is the fractional contribution of the AGN to the total mid-infrared luminosity. So it is ideally placed at tracing AGN activity of any source. Now, we define the so how do we define or where do we define the mid-infrared axis? So this plot shows the distribution of the AGN fraction parameter. For this work, we use the 16th percentile because photometry by itself is not does not place very strong constraints on the AGN fraction. So we want to be very cautious with our values. So the orange distribution shows all the sources, while the maroon distribution shows only the confirmed AGN. As you can see, there the value of 10 power minus 3 seems like a very reasonable value to separate the AGN and the non-AGN sources. Now, we place certain additional tests to make sure that this mid-infrared excess is due to AGN. First of all, we see if the fit is acceptable or not. We calculate the chi-square based on the best fit SED, and then we see if the chi-square lies below the 99 percentile confidence threshold for the given number of photometric bands. So if the source has acceptable fit and a high AGN fraction, then it is an AGN. Otherwise, works have shown that including AGN in the template, that leads to better fits for sources that host AGN. So for this, we fit every source twice, once with AGN and then without AGN. If the chi-square with AGN is significantly lower than chi-square without AGN, we call it AGN. So now step 1 out of the way. For step 2, we want to determine what is a radio excess. So at 150 megahertz, the radio emission is primarily non-thermal synchrotron radiation coming from the stellar processes and jets. You may have heard of the star formation rate radioluminosity relation. For star-forming galaxies, the star formation rate and the radioluminosities are related, form a straight line. We can identify sources as radio excess depending on how far they are straying away from this linearity. So this is the best fit we get from our work. As you can see, it's very linear. Now, to define the precise criteria for a radio excess, we take the difference between the observed radioluminosity and the radioluminosity that is predicted from this relation. So the predicted radioluminosity for a star-forming galaxy. So this distribution looks something like this. The left hand of the distribution can be well fit by a Gaussian with standard deviation of around 0.3 dec. And the right side has an extended tail, which we believe which is definitely due to radio excess sources. So we define a source as radio excess if if the observed radioluminosity exceeds the theorized radioluminosity by more than 0.87 dec, so which corresponds to 3 sigma here. So this line translates to this line in the radioluminosity star formation rate plane. Now that we, so to summarize these two questions, does the source have a radiative mode AGN and does it have a radio excess? If both the answers are no, then the source is a star-forming galaxy. If the source has a radio excess, if the source doesn't have a radio excess, but it has a radiative mode AGN, we call it a radio quiet AGN. Conversely, if it does not have a radiative mode AGN but has radio excess, it's a low excitation radio galaxy. If both the answers are yes, then it's a HARG. So this is what our classification looks like. It's a mix of all kinds of sources, and it's dominated by the star-forming galaxies. Now, comparing it to Best et al. 2023, you can see that overall the classifications look very similar. Look very similar. The principal disagreement is in the number of HARGs, and that is because of the precise definition of where the radio excess classification lies. So diving deeper into the source demographics, this plot shows the fraction. This plot shows the fraction of sources at each in each of the radioluminosity bins. As you can see, the radio faint sources are dominated by star-forming galaxies, which is sort of contrary to what you would think when you would think of a star-forming radio-dominated source. Now, as the radioluminosity increases, you can see that the logs and the hawks start dominating. So the star-forming galaxies dominate up to 25.5, after which the logs become the most dominant class. Now, in the star formation rate plane, you can see that most of the logs are hosted by the quiescent massive galaxies, which is what we would expect the logs to be. However, it is interesting to note that there is a massive, there is also a significant population of star-forming logs. This is very important. This is in agreement with what Best et al. Found, and this has led to follow-up work such as Kondapalli et al. 2022 and a paper which is about to be submitted to Manras in a few days. Now, when it comes to redshift, you can see that the logs, the log fraction peaks at around redshift of 2 here, and then at higher redshift, the radio quiet and the hard populations dominate. So we can, oh shit, sorry. We can confidently say that at higher redshifts, the sources are dominate, the radiative mode sources dominate, and then we can see a transition into jet mode sources by cosmic noon. So with that, I'll jump to my summary. So spectroscopy is still the gold standard when it comes to galaxy classifications. In the absence of spectroscopy, however, integrating multi-wavelength data with radio gives us the second best answers. In this work, we achieved comparable results to previous studies by using a single code, therefore eliminating the time constraints of the previous work. The paper is published. This is the QR code. So for the current work, we are integrating DESI spectra with LOTS photometry, and we are trying to include the BPD classifications with the FAGN-based classification. So if you have any ideas or any suggestions, this is ongoing work. Please give me a shout out. Thank you.
Stas Shabala, University of Tasmania. Thanks, great talk. On your last slide, oh, the one before this, when you talked about, thanks, the plot on the right, the redshift evolution.
Yes.
So there are more Hergs at higher redshifts.
Yes.
Could that be a selection effect? And if so, what sort of selection effect?
So at higher redshifts, it could definitely be a selection effect, because the higher you are, the fainter the brighter the sources you'll be picking up. And I don't think we are we are reaching as high radioluminosity space that that would be dominated by Hawks. So there's definitely, I mean, I'm not able to find the exact word for it, but yeah, the selection effect does come into play. So if we had even longer integration, we would be seeing more Hawks. That's what we believe.
Hi, I'm Harry. I'm a postdoc at Swinburne University in Melbourne. I don't know much about this field, but why are there so many unclassified galaxies in your sample, and what exactly can you tell me about them? Why don't they fit into your population here?
Right. So we adopted a very conservative cut for calling a source which a bad fit. So any source that has a chi-square of more than, it comes out to be something more than 30 or 40. So any source with a higher chi-square, we don't want to trust the star formation rate. So if we don't trust the star formation rates, we can't classify them based on the star formation rate luminosity relation. So that leads to that higher number of unclassified sources. So it could be due to the presence of broadline AGNs. It could be, I think 1,000 of those sources, they don't have redshift estimates. So that's down the drain. Some of these sources are also I think some of these sources are also quasars, which prospector cannot fit properly. So that leads to errors. There are also sources that have very low star formation rates. We also have to be very careful about classifying them because obviously the uncertainties are larger. So we also had to put another cutoff to remove them. So it is a bit of a complicated procedure. So I mean, I think it would be better to discuss this in person after the talk.
All right, so I have two questions. The first is about your L150 megahertz distribution there, the middle plot. Have
Yep.
you compared this to T-Rex simulations?
TNG?
T-Rex.
T-Rex, no.
Yeah, no, okay. Perhaps it would be interesting to see
Okay, yeah.
what the distributions there look like that they predict.
Mhm.
Just for a check on, yeah. And another thing is Prospector. Why that SED fitting code? Why would you select Prospector as an SED fitting code over Magfis or Segal or?
Okay, so broadly there are two reasons, three reasons. First of all, it can model both AGN and it includes AGN templates. So Magfis does not, or at least when I started my PhD, it did not. Secondly, it can model both photometry and spectra on an equal footing. Magfis, Segal, they can't. And my PhD thesis is titled The Science with Weave Low-Far Survey. So we want to be working with photometry and spectra, and Prospector seems to be the best placed tool for that. And the third is the non-parametric star formation history. So when you are what Segal and Magfis and most of these codes, they at least back in 2021, they used to use parametric star formation histories. And if you are tying down the early and the later stages of the star formation history, and if you are assuming a functional form, you are discarding solutions, potential solutions. So you are underestimating the uncertainties. So non-parametric star formation histories are supposed to be more data-driven, and that's why Prospector seemed like a better choice to us.
Okay, thank you, Samir.
Cheers. Thank you.
And the next speaker is
Sorry.
Venkateshwara Ramakrishna.
All right, before it's been posted up, I just want to thank the organizers, both for the session and the conference organizers. I'm Venkatesh Ramakrishnan. I'm a member of the Event Horizon Telescope Consortium, and I'm also PI of this study, which I'm going to be presenting here right now. So what we have seen by now from EHT is we have seen two beautiful black holes, M87 and Sagittarius A star. And what we also know, in one of the variants of M87 is we have seen the polarized image of it with nice sprinklers around it. But leveraging on this result, the objective of this study is transform from what we know of two sources into sort of making of the donut factory, as can be said by all these images that we might able to see in the future. Of course, all these are simulated images based on several parameters. Now, again, to break this down from our parlance, it can be the objective of this study can be put into two cases. One about imaging more black holes in the nearby universe, which is going to be important for us to not just understand the mass, but the shape of the image is also going to tell us about the spin, which is something we all have been longing for a long time. And of course, not to forget the space-time metric, which is more indicative of the general relativity or alternate theories of gravity. The other case, in targets where resolving these sources will not be possible, obviously, the other thing that can still be done is their interaction of the accretion flows with their immediate environment. And even in this case, it's still a possibility that we could draw pretty good constraints of the spin of the accreting systems in the nearby universe. So what's the motivation for all this is, of course, comes in the form of VLBI observations, the EHT finding its success in recent years. You must have heard a lot of talks, this symposium, one recently presented by Randy a few talks ago. Of course, I wanted to mention, I picked this particular slide because it's not only EHT that's driving its success. EHT also gathers its significance from a lot of decadal studies done using array called GMVA, which is a VLBI network observing a 3 millimeter. But the success came in the form of several connector element interferometers, namely ALMA, SMA, and NOIMA, which is of course left out in this figure, but is part of the EHT network. SMA is not part of the, doesn't have a 3 millimeter receiver, hence it's dropped out of GMVA. But it's in the making, and probably we wanted to see that in the next generation EHT missions. What is the major advantage of having all these interferometers is, of course, I mean, with each one of them being a connector element interferometer of its own, by phasing them up, we are going to be synthesizing them as one single dish. And for example, in the case of ALMA, it's going to be acting like about 80-meter dish, which hence making it as the largest dish in the, for example, in the EHT network. And again, phasing up is not something new. It has been done for a long time. For example, it is being done with LBA, where ATCA, the Australian Telescope Compact Array, where when it takes part in the Long Basin Array network, ATCA is being phased up, and so is the case when, if and required, VLA needs to be play a role in VLBA observations. One can request for phased up VLBA as well. But of course, in this case, engineers had to develop the algorithms for the case like ALMA, SMA, and NOIMA, which is what has been driving the success for EHT since 2017. But what has been until the end of 2021 is a system called active phasing, by which we have been able to, the sensitivity was helping us to reach targets as bright as about half a Jansky. However, the major driver for this particular study comes in the form of a passive phasing, which is pretty analogous to phase referencing concept, something which will be reviewed in detail by Maria Rioja and Richard Dodson tomorrow at several talks. So you can listen to that if you want the technicalities of it. But at least by this particular technique and with, what it demands is having a calibrator in the nearby proximity of the source within about 3 to 5 degrees. One can, the sensitivity gets so high that the targets, it's anticipated that you can reach as low as about even 50 to 100 millijanskis. So with this concept, we went further, and what we did, again, in order to pursue this, take this further, was to build a sample of supermassive black holes. We called it as the ether sample. Again, what we did was we started off with something very simple. Again, we took all the existing dynamical black hole masses from literature, thanks to most of you who have contributed that for this study. And in addition to that, we also took all the literature estimates of the stellar velocity dispersions, and using fundamental planes, we sort of extrapolated that. And what our table sort of looks up is something like this. We have the different targets, the distances, and the anticipated photon ring size, which comes from the distance and the mass of the black hole. And of course, the most important thing also being the brightness of the source at the millimeter bands. One unfortunate case, I'm sure a lot of you might have this question is, aren't there any other targets which can be resolved with the EHT? Well, there are a lot of massive black holes in the nearby universe with ring sizes larger than the EHT's, better than the EHT resolving limit. But unfortunately, a lot of them turns out to be rather radio quiet. Hence, again, we are keeping our fingers crossed, hoping that we will be able to find more targets in the near future. So putting all of them in a figure like this, we have the black hole masses and the ring sizes. Of course, it's going to look pretty linear because they are interdependent. As you can clearly see that there are quite a number of sources, and a lot of them, at least to the right of this line, are still based on the stellar velocity dispersion, since they do carry a significant uncertainty. So one of the things we are trying to do is estimating their black hole masses. But at least we hope there will be at least a handful of sources here which might be able to resolve by the EHT in the near future. So what are the things that we are doing right now? Again, before we start off with the EHT observations, is we execute 3 parallel projects. The first one being the obvious thing, estimate the fluxes of these targets at EHT frequencies. And for this, we make use of 3 interferometers, ALMA, NOIMA, and SMA. The reason why we go for interferometers is also might be obvious for some of you. because a lot of these targets might also be having cold gas. Hence, it's important for us to make sure that by using an interferometer, we will be able to probe the non-thermal or probably the core of the galaxy, which are not affected by the dust in these systems. And of course, we also been getting multi-band observations from ALMA, for example, and the reason being that we wanted to also focus on the opacity of the accretion flows or the jet flows in these systems. And the reason is can be explained from these figures here. Because so far, again, we have been driven by the EHT success. We think 1 millimeter, 230 gigahertz is the go-to frequency, if not higher. But we are just hoping that what if there are sources which are already transparent at lower frequencies, like 86 gigahertz, for example, or maybe 120, 115 gigahertz when facilities like NGVLA takes its shape in the future. So hence, for that matter, we are also trying to see, anticipate what the opacity of these systems look like. And you can already see for different opaque systems, how the accretion flows are going to look like for different mass regimes. And the other thing that we are trying to do is, again, to estimate the black hole masses. This is going to tell us where they lie in our figure. Are they going to be, are we able to going to resolve the photon ring, or is it like under massive? Of course, this is affected by the fundamental plane relations. But in this case, what we are specifically doing is we are more eager to get the stellar dynamics mass measurement. And the reason is, again, driven by one of EHT's results on M87, where we found a good agreement with the stellar dynamical mass measurement over gas dynamics. Again, something that we sort of know from literature, where the gas and the stellar measurements are known to be off by a factor of a few or if not more. The other last thing, again, another obvious thing we are trying to do is looking at the X-rays. And in this case, we are particularly looking at new star data, known for its hard X-ray sensitivity, going all the way until 79 kiloelectron volts. And in this case, we are trying to be more in favor of looking at inefficient accretion flows, something that is more, again, indicative of low luminosity AGNs like Sagittarius A and M87. And the reason for that is because, again, taking a simple cartoon of our current understanding of our geometry of accretion flows, so forth, what we know is nearby the supermassive black hole, in one of the cases, the standard case, we know it's characterized by a thin disk. But the other case, like Sagittarius A star, we understand that there is a hot cloud of gas. And I mentioned hot cloud because different groups goes by it in different names. It can be also considered as an ADAF or RAF accretion flows, which is known to be geometrically thick and optically thin. And this is one of the important cases that has been also helping us in terms of interpreting both the images and the simulations. And the reason being that this is going to, again, targeting such systems are giving us hints that we may be able to resolve the accretion flows better. But again, this is something we are trying to iterate over different targets. And we hope to, again, find some better convergence on these targets. So replacing this figure in a different way, again, retaining the photon ring diameter in the x-axis, but converting the y-axis into fluxes, we see a lot of sources here. Of course, all the cyan targets are extrapolations. The one in red are already those that are observed by EHT, and most of it has already been published. But then what is the interesting thing that is marked on this figure are the different resolving limits. One, the existing limit by the EHT, and it's clear, at least based on all the fluxes that we know of, none of these sources can be resolved. Nevertheless, these are the targets we are currently targeting. But then the other two lines are indicative of how significant will be the resolution should we place a telescope on orbiting Earth at either the geostationary orbit or if not further at L2. Hence, we are going to see perhaps about 50 targets or more that's going to be resolved. So yeah, skipping further in the interest of time, just show a few results that we have. Again, so far I've been talking a lot about high frequency observations in the millimeter, but that doesn't mean that low frequency is any bad. It's also going to be indicative of telling us what the jets in these systems are and what the accretion flows are. And we already find from low frequency radio observations that there are a few targets where the flattening that we notice in these systems, which are unlike of any high accreting systems, and again, something that seems to be telling us how these systems are going to be perhaps best candidates for EHT observations in the future. And again, some simulations going to tell us how the opacity is going to be looking at, taking different particle physics into account and electron distribution functions. In this case, we tested some thermal synchrotron models, and then see, again, notice not many sources may be resolved, but again, this depends on the masses and distance estimate. We test their spin by broadband SCD modeling. Again, something that's going to be very useful for us to get a better constraint from a multi-wavelength perspective. And again, a lot of simulations of recent work done by a student, Alice Zhang at Harvard CFA. Again, giving us hints of what we might be able to expect for a broad range of accretion flows. And again, before I leave you with the summary, so what we now have in the GMVA and EHT observations is that we have begun observing all these dozen targets since 2022. Again, one important thing for VLBI is to know how bright these targets are. So we did the feasibility study of them, and we tried to see if we see any fringes or not, as we notice in this plot. At least for a handful of sources where we did see, we have already started to pursue more deeper observations since last year. And yeah, we expect at least these the results to come up more towards the end of the year and next year. So I leave you here with the summary, and happy to return the floor to the speaker. Just share. Thank you.
Any questions? So actually, I got one. So how confident you are about actually putting a telescope, a radio telescope at at a stationary orbit or RL2?
Yeah, well, the work is in progress, at least for space projects. So there are a few experts who can tell you more on that, but yeah, something that's being worked upon.
Any more questions? So, I think we should thank the speaker again.
Thank you.
Giorgio Filippos. The speaker is Georgios Filippos. He's on the web? Online, yes.
Yes.
Okay. Okay, so you can start.
Can you hear me?
I guess we can hear you.
All right, great. Yes, so thank you very much to the organizers. I'm George Parasos, postdoc, the Max Planck Institute for Radio Astronomy in Bonn. And today I'll talk about how black hole jets are launched at multiple scales. And so, as we know, jet launching, acceleration, and collimation are still fundamental unanswered questions. And we can use radio galaxies, such as 384, which I will talk about today, to provide a prime testbed to explore, for example, where the jet base and the black hole location is. Specifically for 384, try to see what the elongated core means, if it's a broad jet base, if it's jet bending, or something stationary like a recollimation shock. And also look at the kinematics of the jet, look at jet launching speed, acceleration, and perhaps non-ballistic motion at play. Very briefly, here's a cartoon of what we think is going on. So we have, of course, the black hole in the center, accreting mass around it, and the two jets are launched from the poles. We already heard today about jet launching scenarios. The two main ones are the Blanford-Nesnajek type of jet, which we see here on the left, which is a narrow jet launched directly from the ergosphere of the black hole. An alternative scenario is a Blanford-Payne type of jet, which is launched from the accretion disk and is therefore broader. And more realistically, of course, it can be a stratified combination of the two, in which we have the central spine, which is moving quickly, surrounded by a slower outer sheet. And this is how it would look like from the side. So we have the magnetic field lines directly connected to the black hole in the BZ scenario, whereas in the BP, they are connected to the accretion disk. And so the way to answer these questions is with millimeter VLBI, because this offers a number of advantages. We can, with millimeter VLBI, peer through self-absorbed regions, explore the physics of the central engine, study the origin of jets, of course, zoom into the heart of radio galaxies, achieving typical spatial scales of less than 0.1 parsec or a few thousand Schwarzschild radii. And for example, at 3 millimeters with the GMBA, we can also get excellent UV coverage in high dynamic range. You can see here on the right how this looks like. We can simulate a telescope the size of 9,000 kilometers in radius. And finally, of course, we can do synergy by doing spectral studies, combining different observing frequencies, and also do broadband multi-wavelength campaigns, combining, for example, the radio observations with X-rays, gamma rays. And so without further ado, let's have a quick look at 3C84, the test bed that we use to see how jets are launched from black holes. Here is a larger scale of this source. On the left, you can see an optical image of 3C84. You can see the bright core and also these filamentary structures around it, which are most likely supported by the magnetic field that is very strong. And on the right, you can see the same source, but in X-rays. And you can also see the radio contours overlaid on it. And very interestingly, as you can see, the contours seem to be more strong where there's an absence of X-rays. So these two darker blue regions are where there's less X-rays than in the green areas. And this might be connected to the fact that the jet is pushing away the intercluster medium and thus creating this so-called X-ray bubbles. And the other interesting observation here is that, as you can see, these two lobes, let's say, are misaligned with the jet axis, which is more in this direction that I'm indicating with the cursor, whereas they seem to curve a bit. This might be connected to some rotation happening, which we'll have a look. If we now zoom into the nuclear region, double-sided jet is revealed. So on the left, again, you can see the optical image, and then when we do 22 gigahertz ground-based VLBI, you can see this these two plumes, which are emitted north and south of the jet, and also some filamentary structures connected to the central part. Now, we also have VLBI in combination with the space antenna. This is the right image, and we can of course see more details here. And if we zoom in even further, we can see that this core region has this elongation that I already hinted at. That's something counterintuitive, I would say, because naively we would think that the way the jet moves in one direction, which is this north-south direction, everything should be aligned with it, but we see that this is not the case. So this is something very interesting that we want to have a look at. Of course, you can also see these two bright limbs, which are connected to this core region. And the same thing can be seen also in polarization. So here on the left, you can see 86 gigahertz images of the source, and the polarized light reveals that this limb brightening is present deep in the core area. I use this red parabola to highlight that. And on the right, you can see 4 images of the core area of 3C84, which are just 1 month apart of each other. And interestingly, you can see how much the polarization changes. So it needs to be kept in mind that this is a variable source, and this is something intrinsic. And so, as I said, we wanted to have a look at the ultimate vicinity of the black hole of 3C84. And that's why we used the Event Horizon Telescope to resolve what it looks like. So on the left, you can see lower frequency images of the same source taken quasi-simultaneously. And of course, the higher the frequency, the better we can zoom into the core region. And then on the right, you can see the EHT model of what this looks like. This is a geometrical model fit of the visibilities. And you can see we have these three components. We again see this allocation. We call them east, west, and core. And to gain even more insight into what is going on there, we also had a look at polarization. So in polarized light, you can see how the core looks like. And the central area where we expect the black hole to be more or less, it's less polarized than the two components framing it, which is expected because we know from theory that the jet should be more polarized than the black hole vicinity. So in that case, we can connect this polarized components to the foot points of the jet, so where the jet is launched. And also we also have the absence of a counterjet, which is also expected for this source, because it has been shown in other studies that there's a free absorbing medium around which obscures. We can then use some formulas which we don't need to focus on right now, just to gain some more insights by combining also all the quasi-simultaneous observations that we had. And if we combine all those, we can gain insights into the magnetic field, which is around 3 to 6 Gauss. We can also investigate how rapidly the black hole rotates, which is has a spin factor of around 1, and is an advection-dominated accretion flow. The magnetization parameter points to a magnetically arrested disk. And overall, this points to a preference of a Blandford and Znajek type of jet launching, which is also consistent with literature. Now, we also wanted to study the entirety of the parsec scale jet, because keep in mind the scales that we looked at before were less than 0.1 parsec. They were around 300 Schwarzschild radii. And to do that, we decreased the observing frequency and took advantage then of the increase in UV coverage. So on the left, you can see the EHT UV coverage that we used for the images that I showed you. And on the right, you can see at 22 gigahertz what UV coverage we can achieve. And so our global European VLBI network observations revealed this limb bright, which you can see here, was also known from observations almost 10 years back, which means that this is consistent. And they reach deep into the compact core region. This also might point to jet certification being at play. Interestingly, we were able to show that these two limbs, this double rail structure that we saw, is also visible in polarized light. This is what you see here on the right. So the color scale, the color bar, is what is the linear polarized flux. You can see that this is visible in the core region. There's also an inner spine detected at the significance of 4 sigma. And finally, if we have a look at the position angle of the electric vectors, they seem to be parallel to the bulk jet flow, which is in this direction at the spine, but perpendicular to it, the rails. So this is another indication that we have this certification at play. And of course, it might also be connected to jet shear or a shock. In order to now interpret our results, we compared them with relativistic magnetohydrodynamic simulations, which is shown here on the right. And these simulations show that our observations are in line with a helical or toroidal magnetic field configuration. This is also seen in the position of the electric field vectors, which again follow the boxed flow at the spine and are orthogonal to it at the limbs. On the other hand, a poloidal field does not reproduce that. So we were able to reject that hypothesis. And overall, this is consistent with the spine sheath geometry. And so if we put all of this information together, then we can assess that the rotating helical filament, which is located within the broader jet, as shown in this cartoon here, may explain everything we saw. The elongation of the core, the jet stratification, and also the jet bends. Of course, we're continuing to study the source with higher resolution observations to try to get more conclusive results about it. And with that, I arrive at my conclusions. So we demonstrated the capability of millimeter BLBI to resolve jets of nearby radio galaxies transversely. We found a highly coherent, strong magnetic field around the central supermassive black hole of 384. We saw that the accretion flow is attraction dominated and magnetically arrested state around the rapidly rotating black hole. The emission, the polarized emission of the core region is also traced by bright glimpses, which are seen also in total intensity. And finally, the position of the electric vector suggests that there's a toroidal magnetic field configuration at play, which is consistent with the spine sheath geometry. And I think I'll leave it at that.
Do we have any questions? Do we have any questions? Do you have any questions about this?
Hi, George. Really great talk. This is Irandi. So in looking at your the fit of the 1.3 millimeter, the EHT data in the 3 components. So one of them, the fractional polarization was at like 80%. Oh, sorry, the one where you're actually showing like
yes,
the geometric.
Yes.
Yeah. So like.
Yeah.
Yeah, that one. So the fractional polarization of that component is like 80%. I thought like that seems like, at least in my head, I have the heuristic of like up to 70% for synchrotron radiation. So how, like, what's the explanation for it being so high?
Yes, of course, you're right. So the thing is, modeling such sparse data showed that there should be a component there which is highly polarized. The uncertainty is very high. It's plus, minus, I would say, 30 to 40%. So the only statement we can make is that there's a highly polarized component that is favored by the model, which can be very high, but doesn't have to be actually 8%.
Okay, thank you.
Any more questions? Okay, so if there are no more questions, we should thank all the speakers. And there is a nighttime hybrid session, purely online, if you're still interested. No, don't come to the venue because it's all on the internet.